The Mercedes G-Class is built with precision inside one of the most advanced automotive factories in the world. From hand-welded steel frames to meticulously crafted interiors, every step combines rugged engineering with luxury detail. Today, we take you inside the production line to see how raw materials are transformed into an icon, revealing the techniques and craftsmanship that bring the legendary G-Wagon to life. Our journey begins deep within the steel supply and stamping operations, far from the glittering finish lines of final inspection. The G-Class starts life as a collection of raw, flat metal panels. These panels, primarily high-strength steel, are delivered to the facility in massive coils, which are unrolled and leveled before being fed into industrial press machines. These presses apply thousands of tons of pressure to shape the steel into the various foundational parts of the G-Class body, such as the floor pan, door skins, roof frame, and iconic flat body panels. The unibody shell is not used in the G-Class. Instead, it's built with a ladder frame chassis, a method more common in heavy-duty trucks. This makes the process both more rugged and more complex, requiring each piece to be perfectly formed to exact tolerances. Once the panels are pressed, laser-guided robotic arms trim and smooth the edges with astonishing precision. Each cut is planned digitally down to the 1/10 of a millimeter, ensuring uniformity across thousands of units. Now we move into the body-in-white phase, the initial stage of structural assembly. Here, the stamped panels are arranged into sub-assemblies. The floor pan, side frames, firewall, and roof supports are meticulously aligned on a series of jig fixtures. These large, articulated steel mounts hold each piece in perfect position for welding. But unlike many modern car factories where robot arms zip through spot welds in a blur, the G-Class body is largely welded by hand. Dozens of skilled technicians, each highly trained, wield welding torches in a choreographed dance of sparks and heat. More than 6,000 welds are performed on each body, reinforcing the vehicle's structural rigidity. As they go, workers constantly inspect joints visually and mechanically, using go-no-go gauges to confirm tight fits and ensure that structural integrity is never compromised. The welding process is a symphony of patience and expertise. Welders must account for heat distortion, managing the order and location of each weld to maintain the geometric accuracy of the body. They use pneumatic clamps, steel rulers, and laser levels to ensure that the angles and lines of the body remain true. It is here that the G-Class's signature upright posture begins to take shape. Those vertical window frames, slab-sided doors, and angular corners that give the vehicle its commanding silhouette. They're all defined and locked into place during this early phase. Once the body is fully welded and structurally complete, it undergoes a process known as metal finishing. This is where skilled craftsmen examine every seam, edge, and panel for imperfections. Small hammers, abrasives, and filler tools are used to smooth out inconsistencies. The goal is to achieve a surface that will accept paint without a single visible ripple or deformity. The attention to detail here is extraordinary. What may seem like an invisible bump to the naked eye will be caught later by paint defects if not resolved. Technicians in this stage often use high-powered overhead lights and fingertip inspection techniques to feel for irregularities. And yes, they still do it by touch. Technology can detect misalignments, but it's the trained human hand that often finds the smallest flaws. Once the body in white has passed inspection, it is ready for paint preparation. But before any color is applied, the shell undergoes a rigorous cleaning process. It is first immersed in a series of chemical baths, alkaline cleaners, degreasers, and deionized water rinses that strip away all traces of oils, residues, or contaminants from the welding and finishing stages. Then it moves into the e-coating process. This is where the body shell is dipped into a giant electrocoating tank filled with anti-corrosion primer. An electrical current is applied, causing the primer to bond to the metal surface at a molecular level. Every nook, crevice, and corner is coated evenly, providing unmatched rust protection. The G-Class was originally built for military duty, and this durability-focused philosophy continues today. After the E-coating, the body is cured in an oven at temperatures around 180 degrees Celsius. The curing hardens the primer and sets the foundation for the paintwork that will follow. Then comes the application of the base coat, color layers, and clear coat, each sprayed meticulously in high-tech painting booths. The factory offers a broad range of colors, from conservative blacks and silvers to vibrant custom finishes from the G Manufacture Personalization Program. Incredibly, many G-Class vehicles receive their paint by hand spraying, not automated robots. This allows greater control and customization for two-tone finishes, matte effects, and hand-masked accents. The painted body then returns to another round of inspections. Factory workers use light tunnels and soft cloths to detect even the smallest specks of dust, paint sagging, or orange peel textures. If needed, technicians wet sand and polish the affected areas manually. This is one of the most time-consuming parts of the process, but it ensures that the G-Class leaves the paint shop with a flawless, mirror-like surface. With the body now painted and prepped, attention turns to the chassis, the rugged ladder frame that defines the G-Class's off-road DNA. Unlike unibody cars, where the structure and body are fused, the G-Class separates these two elements, a design that offers superior strength and modularity. The chassis is fabricated from thick-gauge steel and welded into a rectangular framework with multiple crossmembers and mounting points. It's engineered to endure extreme torsional loads from uneven terrain, rock crawling, and high-speed travel over unpaved surfaces. The entire chassis is then treated with a special powder coating that protects it from gravel, salt, moisture, and mechanical wear. At this point, the chassis begins its mechanical assembly. Giant overhead conveyors lifted into place on a moving assembly line. Suspension components are added first. The G-Class uses a double wishbone front suspension and a rigid rear axle with trailing arms and coil springs, all designed for articulation and ride comfort. Workers mount control arms, install air or coil springs depending on the configuration, and torque each fastener to precise specs using digital torque wrenches that record every application for quality traceability. Drive shafts, differentials, and the transfer case follow next. The G-Class features 3 locking differentials, front, center, and rear, making it one of the most capable factory off-roaders ever built. These components are pre-assembled in sublines and arrive at the main chassis line just in time for installation. Each differential is bench tested before being mounted, and once installed, hydraulic and electronic connections are secured and checked for sealing integrity. Next, the engine and transmission arrive. These powertrains are built separately, typically at Mercedes powertrain facilities, and delivered fully dressed with wiring harnesses, fuel systems, and control modules already in place. A robotic hoist lowers the engine and transmission into the chassis as technicians bolt it down to reinforced subframe mounts. The transmission tunnel is lined with heat shielding and the exhaust system is connected. Stainless steel manifolds, catalytic converters, and mufflers are all aligned with laser guidance systems to ensure proper clearance and vibration isolation. As the powertrain is secured, attention turns to the braking and steering systems. High-performance disc brakes with multi-piston calipers are installed on each wheel hub. Brake lines are routed with stainless steel fittings and then bled using automated vacuum machines to ensure a perfect seal and no air bubbles. The power steering rack is attached and aligned, and its fluid circuits are pre-flushed to remove any contaminants. At this stage, the chassis is essentially a rolling platform, ready to meet the painted body that has been traveling in parallel on a separate line. Continuing our journey into the heart of the Mercedes-Benz G-Class assembly process, we arrive at the moment of mechanical matrimony, a pivotal point known within the factory as the marriage. This step is one of the most anticipated stages in any automotive plant, but here in Graz, it carries almost ceremonial weight. The moment when the meticulously painted body is lowered onto the fully built ladder frame chassis transforms a collection of high-grade parts into what begins to truly resemble a finished G-Class. The process begins with both the body and the chassis arriving at the marriage station on two separate automated conveyor lines. Precision and timing are essential, as the chassis is lined up beneath the suspended body shell. A series of hydraulic lifts and alignment pins begin the delicate work of bringing the two together. Technicians verify multiple reference points using laser measurement tools to ensure the body mounts align perfectly with the corresponding points on the chassis. The process may appear straightforward, but in reality, the tolerances are extremely tight, within a single millimeter. Any deviation could lead to misaligned panels, noisy interiors, or handling inconsistencies. Once the alignment is verified, the body is carefully lowered using a multi-axis robotic gantry system. Specialized bushings are inserted between body and frame to absorb vibrations, and bolts are torqued down using synchronized electric torque tools. These tools not only apply the correct force, but also record each torque event digitally for traceability. In total, dozens of mounting points are secured during this stage, creating a permanent bond between body and chassis. With the vehicle now structurally complete, the next steps shift focus to the installation of electrical systems and interior components. The G-Class is known for its advanced technology, luxury appointments, and off-road capability, all of which require an intricate network of electronics. Wiring harnesses are delivered to the line pre-assembled and bundled according to specific vehicle configurations. Each harness includes connectors for power distribution, lighting, infotainment, sensors, airbags, and the drivetrain management system. Installation of these harnesses is done mostly by hand due to the complexity and variability of options in each vehicle. Workers snake thick bundles of cables through the body structure, routing them through the firewall, behind the dashboard frame, under the floor, and along the roof rails. Clamps and cable guides ensure the wiring remains secure and doesn't rattle or chafe over time. Diagnostic computers are connected at this stage to confirm continuity, check for shorts, and verify module communications over the vehicle's CAN bus network. While this is happening, the HVAC system is assembled and installed. This includes the heater core, evaporator unit, blower fans, and electronic control motors that adjust airflow and temperature zones. The G-Class features multi-zone climate control, so ducting is routed with exacting precision through the dash, footwells, and rear cabin areas. Once the climate system is in place, the dashboard sub-assembly is installed as a single module. This enormous component includes the infotainment screen, control buttons, ambient lighting strips, and the central air vents. Workers use vacuum suction lifts to guide the dash into place without damaging the painted surfaces or soft leather trim. Now comes one of the most craftsmanship-intensive stages in the entire production, the installation of the interior. Unlike many mass-produced vehicles that use synthetic fabrics and machine-mounted panels, the G-Class is fitted largely by hand, using real materials: leather, wood, aluminum, and piano black lacquered plastics. The seats are built separately and upholstered using hides that are individually inspected for imperfections. Skilled trimmers sew the leather together, using double stitching patterns that match the exterior color or the customer's specification. Once finished, the seats are bolted into the vehicle with electronic seat module calibration to ensure proper memory function and lumbar support. Door panels follow next, These are assembled in parallel stations where components like speaker grills, switches, ambient lighting, and leather inserts are bonded together before being mounted. Each panel is carefully pressed into place and tested for fit, sound insulation, and tactile feedback. The sound of a G-Class door closing is legendary, an unmistakable mechanical clunk that speaks to solidity. Achieving this sound requires a precise interplay of hinges, rubber seals, door weight, and locking mechanism geometry. Carpeting, floor mats, headliners, and trim moldings are next. Workers stretch and press these components into place using heat guns and hand rollers to ensure wrinkle-free surfaces and tight fits. The sunroof assembly is dropped in from above and sealed with multi-layer gaskets to prevent leaks. All the while, every stage includes quality inspections using both visual checks and functional tests. Is the stitching even? Does the infotainment system respond instantly to input? Is the rear seat heating element warming to spec? These aren't afterthoughts, they're checked and verified at every step. With the interior mostly complete, attention now turns to the installation of exterior finishing components. This includes the lighting systems, trim pieces, bumpers, grills, and the wheels and tires. Headlights and taillights are delivered in sealed packaging and installed using torque-controlled tools to avoid over-tightening. Each lighting unit is powered on and subjected to an alignment procedure that ensures optimal beam projection. The G-Class often includes LED matrix lighting, so precise calibration is required to ensure adaptive lighting functions correctly on the road. The bumpers, both front and rear, are more than decorative. They contain impact absorbers, parking sensors, and, in some models, radar modules for adaptive cruise control. These systems must be aligned with the vehicle's central ECU and tested for accuracy. The grille, which houses the iconic Mercedes three-pointed star, is mounted next, followed by trim pieces such as side skirts, fender flares, and the protective body cladding that's especially important for off-road variants. Wheels and tires are mounted towards the end of this phase. Each tire is balanced individually before mounting to minimize road vibration. The G-Class uses either 18-inch or larger wheels, depending on the model, and all are fitted with performance all-season or off-road tires. Lug nuts are torqued in a star pattern and then double-checked by a second technician for safety. The signature rear-mounted spare wheel is added last, requiring special reinforcement brackets to support its considerable weight. At this point, the vehicle is externally and internally complete, but it hasn't yet proven itself ready for the road. That's where the end-of-line testing begins. First, each vehicle is rolled onto a chassis dynamometer for a systems check. This stationary rolling road allows technicians to simulate driving conditions without the vehicle leaving the factory. Engines are started and revved through a range of RPMs. The transmission is cycled through its gears. Braking systems are tested under controlled load. Onboard diagnostics scan every system for fault codes, and calibration values are adjusted in real time. Next, the G-Class is taken into the water testing booth, a sealed chamber where high-pressure water jets blast the vehicle from all angles. This simulates heavy rainfall and river fording to confirm that all seals and gaskets are intact. Doors, windows, the sunroof, and even antenna mounts are tested for ingress. Any leaks are flagged for immediate remediation. Following the water test, vehicles are subjected to a visual inspection tunnel with multi-angle lighting. Here, inspectors walk around each unit, examining body panel gaps, paint reflections, wheel alignment, and emblem placement. Mirrors are adjusted, wiper blades tested, and final protective films removed. Finally, the G-Class is driven onto a short test track either inside or just outside the factory. This final road test includes a variety of surfaces: cobblestones, incline ramps, sharp turns, and slalom sections. Trained drivers listen for abnormal noises, feel for steering alignment, and evaluate ride quality. Any deviation from spec sends the vehicle to a special adjustment area for corrections. Only once all tests are passed does the vehicle receive its final factory seal of approval. Even then, however, the process isn't over. Depending on the destination, additional country-specific requirements are installed. These may include compliance labels, GPS regional settings, localized safety equipment, and left or right-hand drive adjustments. Paperwork is finalized, including the build sheet, quality inspection records, and shipment documentation. The vehicle is then either driven onto a covered transport truck or loaded into a sealed container for overseas shipping. Now that the G-Class has completed its rigorous in-factory birth, a process involving welding, painting, assembly, and exhaustive quality checks, it embarks on the next critical phase of its journey: preparation for global distribution. This phase, though less visually dramatic than robotic welders or precision-aligned dashboards, is nonetheless a feat of coordination and logistics. The moment a G-Class rolls out of the Magna Steyr facility in Graz, Austria, it transitions from handcrafted engineering marvel to a globally positioned product bound for showrooms, private collections, mountain trails, or inner-city avenues. But before it reaches any of these, there is still a tremendous amount of effort that goes into protecting, staging, and transporting each unit with the same care and attention to detail used in its creation. Once a G-Class vehicle has passed its final road test and received its full quality release documentation, it is driven under its own power to the staging area adjacent to the main plant. Here, specially trained logistics personnel begin the final detailing and protection process. Although the vehicle is fully finished, there is a layer of preparation necessary to ensure it survives the rigors of global shipping. Protective films are applied to sensitive areas: the hood, roof, door sills, mirrors, and corners of the bumpers are covered with temporary plastic guards that resist scratches, UV exposure, and road grime. The alloy wheels are often wrapped in foam liners or protective rings to prevent damage from transport straps or accidental impacts during loading. Interior surfaces are also shielded with plastic covers over the seats, infotainment screens, and floor mats. Every vehicle is now tagged with a unique, VIN-linked logistics barcode, which details its destination, shipping method, port of entry, and delivery window. This data is integrated with Mercedes-Benz's global tracking system, allowing every stakeholder, from plant logistics to overseas dealerships, to monitor the car's location in real time. Depending on its final destination, the G-Class may undergo additional region-specific programming. For example, a vehicle bound for North America will be loaded with US-specific emissions calibrations and compliance documentation, while one heading to the Middle East might receive enhanced climate control settings and reinforced dust filtration for desert conditions. Next, the vehicle is routed to one of several outbound transport modes. For European customers or regional delivery, G-Classes are typically driven onto covered car haulers, large multi-deck trucks designed to transport 6 to 8 vehicles at a time. These trucks have air ride suspensions to reduce vibrations and protect the delicate ride height sensors and chassis calibration. For vehicles headed abroad, the process is more elaborate. The G-Classes are driven into rail cars or loaded into intermodal shipping containers, which are then routed to seaports like Bremerhaven in Germany or Koper in Slovenia. At the port, each container or open-deck vessel is handled with specialized cranes and ramps that minimize jostling. It is worth noting that many G-Class models, particularly Special Edition or G Manufaktur builds, are transported in sealed containers to prevent salt spray, sun fading, or theft. The voyage by sea can take several weeks. For example, vehicles headed to North America might pass through the English Channel, cross the Atlantic, and dock at ports like Baltimore or Brunswick. Once at port, they are processed through customs, emissions, and safety verification. all under the oversight of Mercedes-Benz regional distribution centers. Then comes a second round of quality control, sometimes called a PDI or pre-delivery inspection. This includes checking tire pressure, recalibrating navigation systems to the local GPS constellation, adjusting language and date formats, and inspecting the vehicle for any damage incurred during shipping. If a vehicle has traveled thousands of kilometers by rail, truck, and sea, this inspection is crucial to maintain the brand's reputation for perfection. Once cleared, the G-Class is dispatched to its final destination: a dealership, fleet customer, private buyer, or regional collection center. Even here, the aura of exclusivity surrounding the G-Class continues. Many buyers opt for specialized white glove delivery, wherein the vehicle is transported by single-car covered trailer and presented with ceremonial fanfare, unveiling cloth, branded key boxes, and sometimes a personal orientation session with a brand specialist. The delivery experience is designed to match the vehicle's pedigree, but beyond the logistics and visual pageantry, what truly makes the G-Class remarkable is that even after all of this effort, the vehicle is still, at heart, a rugged, off-road tool. Every single G-Class, whether destined for a downtown penthouse or a mining operation in Siberia, is built to the same foundational spec: full-time four-wheel drive, locking differentials, a 2-speed transfer case, and a ladder frame that could survive military deployment. That's the irony and the charm of the G-Class. It's capable of climbing a 45-degree incline, fording rivers, and navigating icy switchbacks, yet it will just as often be used to roll quietly over cobblestones in Monaco or park beneath luxury boutiques in Dubai. The factory doesn't know what fate awaits each G-Class, and it doesn't matter. Each one is engineered for extremes, regardless of how pampered its life may be. Now, let's take a moment to consider the people behind this machine. While many modern automotive factories are fully robotic and optimized for scale, the G-Class production line retains an unusually high proportion of human labor. Over 1,500 skilled workers at Magna Steyr contribute to its assembly, many of them having decades of experience with the model. Their knowledge, much of it gained through repetition, mentoring, and attention to the tactile feedback of materials, is irreplaceable. They know the right torque by feel. They can spot a millimeter-wide gap from across the room. In a time where artificial intelligence and robotics are reshaping the manufacturing landscape, the G-Class stands as an example of how artisanal skills still hold tremendous value. This blend of traditional craftsmanship and modern precision engineering is particularly evident in the G Manufacture program. Here, customers can personalize nearly every aspect of their G-Class, from more than 30 exterior paint killers to a wide range of leather hues, stitching patterns, interior trims, and wheel designs. If a buyer wants orange leather with green piping and a matte olive exterior, they can have it. These builds are not separated into another facility. They're integrated into the main production line with designated bays where craftsmen apply these one-off features by hand. This level of customization presents huge logistical challenges, matching materials to build slots, keeping non-standard parts in stock, and maintaining quality across thousands of permutations. Yet the factory has embraced this complexity as a way to deepen the bond between owner and vehicle. Meanwhile, let's not forget the rigorous quality control that continues to influence every element of the G-Class's construction. For example, every powertrain used in the G-Class, whether the twin turbocharged V8 in the AMG variant or the inline-6 in the standard model, undergoes cold testing prior to installation. In cold testing, engines are spun up using electric motors without firing them, while sensors measure oil pressure, bearing resistance, valve timing, and sealing. This ensures that only powertrains meeting exact tolerances make it to the assembly floor. Similarly, each differential assembly is bench tested for noise and balance before integration into the vehicle. It's not enough for components to fit. They must perform to exacting standards. Even paint color undergoes scientific scrutiny. After application, each painted body is checked using spectrophotometers, special instruments that detect even the slightest variation in hue, brightness, and saturation. This is especially important when replacing panels after damage or repair. Consistency in color across different batches of paint and lighting conditions is notoriously difficult. Yet, Mercedes insists on millimetric perfection, even for colors that might only be chosen by 1 in 1,000 customers. It's this obsessive attention to detail that makes the G-Class stand out, and it's why its production process is stretched over more than 100 hours per vehicle. Where other vehicles are designed for efficiency, the G-Class is designed for excellence. Every step, from welding to upholstery, from software calibration to final wheel alignment, is geared toward creating something more than just a car. It's a statement of what happens when engineering, tradition, and passion come together under one roof. The production of a Tesla vehicle begins long before any car takes shape on the assembly line. Deep within the vast expanse of a Tesla gigafactory, a meticulously orchestrated sequence of processes brings together raw materials, robotics, and human ingenuity to transform aluminum, lithium, silicon, and countless other elements into one of the most advanced electric vehicles on the planet. From the first bolt of sheet metal to the final pixel on the touchscreen interface, every component is born of a vision rooted in automation, precision, and sustainability. We begin with the raw materials that will ultimately form the structural skeleton of the car. Aluminum coils. These massive, industrial-grade aluminum rolls are delivered to the stamping facility in pre-cut widths and are carefully inspected for thickness consistency, surface finish, and chemical composition. Tesla predominantly uses high-strength aluminum alloys for many of its structural components due to their lightweight yet durable properties. These alloys are crucial to achieving Tesla's performance goals without sacrificing efficiency or safety. As each coil is unspooled, it is fed into a massive blanking press, a machine capable of cutting large sheets into specific dimensions called blanks. These blanks, often the size of a car door or hood, are prepped for the stamping process, where one of the most visually dramatic parts of the car's creation takes place. The stamping area, often housed in its own building due to the sheer vibration and noise, is where enormous dies, precision-engineered molds weighing several tons, shape these blanks into panels that will form the body-in-white structure of the car. Each die is lowered into a stamping press, often a servo-driven press with forces exceeding 5,000 tons. These machines exert immense pressure in milliseconds, forming the aluminum blank into complex geometries. Multiple stages of stamping may be needed for a single panel, including draw, trim, pierce, and flange operations. After stamping, robotic arms lift and transfer the formed panels onto conveyor belts, directing them to a quality inspection zone where laser scanners and human inspectors check for warping, stress marks, or micro cracks. Any deviation from tolerance can compromise fit or function and is promptly rejected or reworked. While the body panels are being shaped, another process begins deep inside the battery cell manufacturing area. Tesla, being vertically integrated, produces many of its own lithium-ion battery cells. Raw materials such as nickel, cobalt, manganese, and lithium carbonate are transported into specialized mixing tanks where they undergo slurry formation. These slurries are spread onto copper and aluminum foils, which are then dried in a vacuum oven to form electrodes. Once the electrodes are prepared, they are calendared, flattened to precise thicknesses, and wound or stacked into cylindrical, pouch, or prismatic cells depending on the vehicle model. Each cell is filled with electrolyte solution and hermetically sealed in a dry room to prevent moisture contamination. which could compromise safety or performance. These cells are then loaded into battery modules using robotic pick-and-place arms, which align and connect the terminals with extreme accuracy. The modules are assembled into packs, which include integrated cooling channels, structural support, and electronic control units. These battery packs will eventually be installed into the vehicle's underbody, providing both power and structural rigidity. Back in the body shop, the stamped aluminum panels are robotically welded and riveted together to form the body in white, the term for the car's skeletal shell before any paint or interior components are added. Tesla employs a combination of laser welding, spot welding, and structural adhesive bonding to fuse panels together with minimal distortion and maximum strength. Hundreds of robotic arms suspended from overhead gantries work in synchronized motion, welding, clamping, positioning, all choreographed with software that can adjust in real time based on tolerances and feedback. Laser scanners constantly monitor joint integrity and positional accuracy, ensuring that each weld is correctly formed and precisely located. The body in white at this stage is a gleaming raw aluminum shell, unpainted but fully formed, with all major exterior panels in place, including doors, hoods, and trunk lids, which are often removed and processed separately for better access and quality control. The next destination for the body is the paint shop, one of the most complex and environmentally controlled areas of the entire factory. Before painting can begin, the aluminum body must undergo a chemical pre-treatment process that removes oils, residues, and impurities. This is achieved by submerging the body in a series of baths, alkaline cleaners, deionized water rinses, and ultimately a zirconium or phosphate-based conversion coating that promotes adhesion and corrosion resistance. After drying in an oven to eliminate residual moisture, the body moves into the electrocoating tank, or e-coat stage. Here, the entire shell is submerged in a bath of electrically charged paint particles, which uniformly coat every crevice and interior cavity, ensuring anti-corrosion protection even in areas never visible to the customer. The body is then baked in a curing oven to harden the coating and prepare it for the next layers of paint. The painting process involves multiple coats: primer, base coat, and clear coat. Each coat is applied in sealed spray booths using high-precision atomizing robots, which follow programmed trajectories to ensure even coverage. Advanced electrostatic spray techniques are used to minimize overspray and improve efficiency. After each coat, the vehicle passes through a series of flash and bake ovens to dry and cure the paint, creating the high-gloss finish Tesla vehicles are known for. Once painting is complete, the body heads to the general assembly area, where it begins to transform from an empty shell into a fully operational vehicle. But before any parts are installed, the body undergoes another round of rigorous inspections. Laser alignment systems, gap and flush measuring tools, and robotic probes verify dimensional consistency across every surface. Any discrepancies are flagged and corrected before proceeding. Simultaneously, thousands of components are arriving from various sub-assembly lines and suppliers, including the interior trim, seats, dashboards, glass, wiring harnesses, and powertrain modules. These parts are delivered using automated guided vehicles, AGVs, that navigate the factory floor using embedded magnetic strips or LiDAR-based systems, ensuring just-in-time delivery with minimal human handling. The interior assembly begins with the installation of wiring harnesses, which are laid throughout the vehicle like a nervous system. These harnesses, containing kilometers of wire, are clipped into designated paths along the floor, pillars, and roof. Robots and human technicians work together, ensuring connectors are correctly routed and terminals are securely fastened. Next, the HVAC components, dashboard structure, and infotainment systems are installed, followed by airbags, sound insulation, and seat frames. At each step, torque-controlled tools and digital confirmation systems ensure that every fastener meets the required specification. The vehicle's panoramic glass roof, a signature element of Tesla's design language, is then lowered into place using vacuum suction lifters and laser-guided alignment tools. A two-part adhesive is applied by robotic nozzles to create a watertight seal. The doors, previously processed separately, are reattached and calibrated to ensure perfect alignment and smooth operation. Tesla's frameless door design and automatic opening features require particularly tight tolerances and sensor calibration. With the interior taking shape, the vehicle proceeds to powertrain integration, where the battery pack, assembled and tested in a parallel process, is lifted by robotic jigs and bolted into the vehicle's underbody using a sequence of torque-controlled actuators. The drive units, whether dual or tri-motor, are then installed onto the front and rear subframes, connected via suspension arms and motor mounts that are pre-aligned using precision fixtures. With the battery pack securely mounted and the drive units in position, the vehicle is now ready to undergo one of the most critical transitions in the entire manufacturing process: electrical and software activation. While the car may appear nearly complete, it is still lifeless. No lights, no screen activity, no sensor communication. This stage, often referred to as initialization, is where the vehicle essentially takes its first breath. A technician connects a diagnostic interface to the vehicle's central computer, usually via a secure data port under the dash, and uploads the foundational firmware that activates the vehicle's electronic control units, or ECUs. Each Tesla contains dozens of ECUs distributed throughout the chassis, responsible for everything from motor control to autopilot systems, battery thermal regulation, infotainment, and safety monitoring. Tesla's approach to software architecture is notably centralized compared to traditional automakers. Instead of relying on fragmented systems developed by various suppliers, Tesla has developed an in-house software stack that enables over-the-air updates, real-time diagnostics, and direct integration between mechanical systems and the vehicle's neural net. Once the firmware is loaded, a cascade of subsystems begins to power on. The touchscreen illuminates for the first time. The instrument cluster boots up. Cameras begin streaming to internal diagnostics. Every sensor, switch, and relay goes through a self-check process that verifies communication with the vehicle's central gateway. Any issues, such as a disconnected wire, a miscalibrated radar unit, or a sensor failure, are immediately logged for remediation. At this stage, even something as minor as a single LED malfunction will halt the progression until it's resolved. Next, attention turns to calibrating the advanced driver assistance systems. Tesla's autopilot suite relies heavily on an array of forward, rear, and side-facing cameras, ultrasonic sensors, and radar or LiDAR, depending on the model and hardware iteration. These units must be precisely aligned within the bodywork to ensure accurate environmental perception. Calibration is not just mechanical, but also algorithmic. As the vehicle is rolled into a controlled calibration zone, a series of reference panels, patterns, and 3D markers are placed around the car. Cameras are activated, and software compares live imaging data against known coordinates to fine-tune the visual input. The system will not pass if even a single camera is slightly skewed or obstructed. Following this, the wheels and tires are mounted, another process where automation and precision intersect. Each wheel assembly, comprising the tire, alloy rim, TPMS sensor, and balancing weights, is prepared in an adjacent sub-assembly cell. Robotic arms select the correct wheel variant depending on trim level and mount it onto the vehicle's wheel hub using torque-monitored tools. Once installed, the wheels are not yet fully ready for the road. They must be aligned. Wheel alignment takes place on a dedicated platform, where laser or camera-based alignment tools measure caster, camber, and toe angles in real time. Adjustments are made on the spot using robotic wrenches that turn suspension bolts until readings fall within micrometer level tolerances. Proper alignment is vital, not only for performance and safety, but also for autopilot accuracy, as steering bias or drift could interfere with the vehicle's self-driving capabilities. Now we arrive at one of the most impressive parts of Tesla's assembly process: final assembly verification and end-of-line testing. This begins with a full-body water intrusion test. The completed vehicle is driven, or in some cases, automatically transported, into a sealed chamber known as the water test booth. High-pressure nozzles blast the car from all directions, simulating rain, puddle splashes, and pressure washing. Sensors inside the cabin monitor for even the slightest moisture intrusion. Any leak, even a trace around the door seals or underbody joints, results in a stop and targeted repair. Once the vehicle passes the water test, it moves into dynamic testing. But before that can begin, it must first pass a rolling road diagnostic check. The vehicle is positioned on a set of rollers that simulate driving conditions. Here, Tesla technicians run through a wide range of operational checks. Motor response is tested across a variety of simulated terrain profiles. Regenerative braking systems are evaluated to confirm energy recovery rates match expected values. HVAC systems are activated to check for proper airflow, temperature regulation, and acoustic performance. Inside the cabin, the touchscreen interface undergoes a systems integrity test. Each menu, function, and button is activated in sequence. The infotainment system is tested for connectivity to Tesla's software servers. Navigation modules are initialized. Bluetooth and Wi-Fi antennas are pinged. Microphones and speakers are checked for distortion or static. The cabin camera, located near the rearview mirror, is tested for focus and response to light changes. The glove box, front latch, trunk motors, and window regulators are also checked for proper operation and speed. After static diagnostics, the vehicle is finally ready for its low-speed dynamic test. On-site test tracks, usually located adjacent to or within the Gigafactory premises, allow each vehicle to undergo a short but comprehensive road test. The driver is usually a trained Tesla technician who runs the car through a prescribed routine: acceleration from 0 to moderate speeds, emergency braking, tight cornering, and high-speed lane changes. This test evaluates suspension response, noise levels, steering feel, and drivetrain behavior under real load conditions. The vehicle's software continues to log performance data throughout the drive, flagging any anomalies. After returning from the test track, the car enters the final visual inspection area. Here, a team of human inspectors armed with light panels, bore scopes, and digital checklists reviews every visible surface inside and out. Paint quality is scrutinized for orange peel texture, swirl marks, or dust nibs. Panel gaps are measured by hand and with laser gauges. The interior is inspected for material alignment, stitching accuracy, and uniform texture. Every single button, vent, trim piece, and fixture is physically touched and verified. If the vehicle passes this multi-layered gauntlet of inspections, it moves into what's known as pack out, the final preparation area before shipment. Here, the car receives its VIN label, ownership documentation, and destination configuration. This is where region-specific software settings, navigation maps, and language preferences are loaded. The final battery charge is administered, usually to around 90%, before the vehicle is powered down and prepared for transport. Each Tesla is now ready to leave the factory, but even this step is a study in logistical precision. Automated systems coordinate the movement of completed vehicles from the final inspection bay to outbound logistics. Depending on destination, the vehicle may be loaded onto a covered rail car, placed into a secure car carrier, or transferred to a nearby delivery hub. RFID tags embedded in the vehicle identify it to tracking systems that monitor its journey to the customer. It is important to note that Tesla's manufacturing ethos is grounded in continuous improvement. Unlike traditional automakers that rely on annual model cycles, Tesla frequently changes its assembly lines in real time, updating hardware or processes based on production learnings, user feedback, and software improvements. This philosophy means that even within the same week, two identical models may have subtle differences in componentry, firmware version, or assembly methods. These continuous upgrades are made possible by Tesla's heavy reliance on vertical integration and factory-level data analytics. Every torque wrench, sensor, robot, and diagnostic station feeds data into a centralized factory control system. Engineers analyze this data daily, making adjustments to improve efficiency, reduce rework rates, and enhance vehicle quality. This feedback loop between digital twin modeling, live production, and field performance is one of the reasons Tesla has been able to scale quickly while maintaining product innovation. With the vehicle now fully assembled, inspected, and approved, it embarks on the final leg of its journey: delivery to the customer. Whether arriving at a showroom, a regional distribution center, or directly to a driveway via Tesla's direct delivery program, the finished product represents not just a vehicle, but the culmination of thousands of interconnected systems working in harmony, each with millisecond-level precision, each tuned for performance, safety, and the future of mobility. Once a Tesla vehicle has cleared its final inspection and receives its shipment authorization, the journey from the Gigafactory to the customer begins. Unlike conventional auto manufacturers, which often rely on third-party dealership networks and extensive warehousing chains, Tesla's direct-to-consumer delivery model has radically simplified and streamlined this phase. Yet, behind that apparent simplicity lies a highly coordinated logistical infrastructure, optimized to handle the massive volume of vehicles produced daily across multiple global factories. At this stage, the vehicle is routed into a specialized outbound logistics yard, a designated section of the Gigafactory site, or an adjoining facility engineered specifically for the staging, sequencing, and transportation of finished vehicles. Each car is tagged with a digital shipping label that contains its vehicle identification number, model variant, color, wheel configuration, destination, and special instructions such as left-hand versus right-hand drive. This digital manifest is cross-referenced with Tesla's centralized logistics control software, ensuring that each car is placed into the correct regional batch for dispatch. Automated tug vehicles, similar to those used in airport ground operations, tow trailers of Tesla vehicles into position. If the vehicle is destined for domestic delivery, it is typically loaded onto a car carrier truck designed to hold 7 to 10 units. These carriers are scheduled to depart in tightly timed intervals, with software routing each truck for the most efficient delivery path based on real-time traffic, weather, and destination inventory levels. For international shipments, the process shifts slightly. Vehicles bound for overseas markets are loaded onto rail cars or container haulers that transport them to port facilities. At the port, the vehicles are driven onto roll-on/roll-off ships, a type of cargo vessel with built-in ramps and internal decks specifically designed for transporting cars. Each Tesla is parked and secured inside the vessel, often alongside other vehicles of the same batch, in a configuration that minimizes offloading time upon arrival. Throughout this journey, every vehicle remains digitally visible to Tesla's logistics team. GPS tags, onboard cellular connectivity, and carrier integration systems allow real-time tracking from the moment the vehicle leaves the plant to the moment it is delivered to the end customer. This level of transparency enables Tesla to forecast delivery windows with a high degree of accuracy and proactively resolve issues like weather delays or customs bottlenecks. Meanwhile, Tesla's delivery centers and service hubs are preparing to receive the vehicles. These locations, often converted warehouse spaces or minimalist showrooms, act as regional fulfillment points. Upon arrival, each vehicle undergoes a final pre-delivery inspection. This includes checking tire pressures, topping off windshield washer fluid, confirming that the software version is current, and ensuring the paint and interior remain in pristine condition. The protective coverings applied during shipment, such as plastic seat covers and foam door guards, are removed, and the car is detailed for presentation. If a customer has opted for Tesla's home delivery option, the vehicle may be dispatched from the delivery center directly to the buyer's driveway using either a flatbed or a mobile technician. Tesla's minimalist approach to delivery day often involves minimal paperwork, since much of the ownership transfer process is handled digitally ahead of time. Customers sign final documents electronically, receive a tutorial on using their new vehicle via the in-car interface or mobile app, and are given access to Tesla's expansive digital support ecosystem. But delivery is not the end of the story. It's merely the handoff point between manufacturing and long-term ownership. Tesla's commitment to post-production support is tightly integrated into its digital platform. The same software and hardware systems that facilitated the car's birth on the factory floor now serve as tools for its ongoing evolution. Over-the-air updates are one of the most defining characteristics of the Tesla ownership experience, and they depend on a robust ecosystem of remote diagnostics, data collection, and machine learning feedback loops. Every Tesla on the road constantly reports anonymized performance data back to Tesla's servers. This includes battery health, motor efficiency, navigation anomalies, autopilot behavior, sensor readings, and even software bugs. Engineers at Tesla's headquarters use this data to refine algorithms, push updates to correct inefficiencies, and enhance safety features, all without the owner needing to visit a service center. This dynamic software lifecycle, enabled by the tightly coupled manufacturing and software teams, makes Tesla vehicles unique in their ability to improve long after leaving the factory. Meanwhile, Tesla's service infrastructure continues to grow alongside its production volume. Instead of relying entirely on traditional service centers, Tesla employs a mobile service strategy wherever possible. These service vans are equipped with diagnostic tools, replacement parts, and certified technicians who can perform a wide range of repairs or updates at the customer's location. The ability to diagnose and even preemptively fix issues before they affect the driver is rooted in the precision and data fidelity achieved during the original manufacturing process. Looking back toward the factory, it's important to understand how Tesla's architectural philosophy supports this entire life cycle. Every gigafactory is designed not just to build vehicles, but to serve as a data hub, a testing ground, and a self-improving machine. These plants are built with flexibility in mind, using modular assembly lines that can be reconfigured on the fly. Instead of fixed conveyor belts, Tesla often uses autonomous mobile robots and smart material flow systems that can reroute components or vehicles as production needs change. The Gigafactory floor is not one continuous line, but a series of interconnected stations. Each one is equipped with sensors, machine vision, and feedback modules that report into a central factory operating system. This system not only tracks current production metrics, but also simulates process optimizations. For example, if a torque reading at a robotic arm consistently falls within the low-end threshold, engineers can be alerted and update the robot's behavior before a quality deviation even occurs. This predictive control approach reduces downtime and increases first-pass yield, meaning more vehicles pass inspection on the first try without needing rework. Vertical integration plays a critical role in making this system work. Tesla doesn't just assemble parts, it manufactures many of them. From battery cells to electric motors, from infotainment chips to firmware code, Tesla has brought traditionally outsourced operations in-house. This reduces dependency on suppliers, shortens feedback loops, and allows the company to innovate rapidly. For instance, if a new battery chemistry is developed in Tesla's R&D lab, pilot-scale production can begin almost immediately within a section of the existing Gigafactory, without the need for third-party approval or infrastructure overhaul. Even Tesla's supply chain reflects this philosophy of speed, control, and adaptability. Critical materials like lithium, nickel, and cobalt are sourced through long-term contracts with mining operations. And in some cases, Tesla has invested directly in extraction or refinement operations. These materials are routed directly to gigafactories or regional production hubs, bypassing many of the bottlenecks that affect traditional automakers who rely on complex supplier tiers and international freight forwarding. This system is further enhanced by Tesla's real-time digital twin architecture, a virtual replica of the entire manufacturing process. Every machine, part, and process is mirrored in a digital environment that can simulate disruptions, forecast efficiency gains, and run hypothetical scenarios. Want to test how a new weld technique might affect throughput? The digital twin can simulate that change in minutes, allowing engineers to make data-backed decisions that translate directly into physical adjustments. Through all of these layers, physical infrastructure, software integration, vertical manufacturing, and delivery logistics, Tesla has redefined what modern automotive production looks like. It's not just about building cars, it's about building a system that builds itself smarter with every iteration. Every vehicle produced feeds data back into this system. Every manufacturing anomaly becomes a learning opportunity. Every software update enhances not just the product, but the factory's ability to produce the next one even better. What this means is that the Gigafactory isn't a static building. It's a living organism, a self-correcting, self-improving entity designed not only to produce cars, but to redefine what a car even is in the age of autonomy, electrification, and artificial intelligence. And at the center of this vision lies a carefully choreographed dance of machinery, people, data, and innovation, all working in harmony to create not just a vehicle, but a new standard for the global auto industry. Inside a Tesla Gigafactory, perhaps the most mesmerizing and defining visual is the near-symphonic choreography of robots working in harmony. Tesla employs tens of thousands of industrial robots across its global facilities, many sourced from automation giants like KUKA and FANUC, and many others developed in-house. But these aren't the slow, single-arm welders of traditional auto plants. These are high-speed, multi-axis machines operating in tightly coordinated clusters that resemble mechanical dance troupes, fast, precise, and relentlessly efficient. The bulk of these robots are deployed in the body shop, where raw stamped panels are joined to form the body in white. Here, multiple robot arms work within inches of one another, one positioning a panel, another applying structural adhesive, and a third completing a weld, without ever colliding. This level of spatial awareness is made possible by a digital supervisory system that orchestrates each motion path in microseconds. Each robot is fitted with a suite of sensors, including force feedback, proximity detectors, and sometimes even cameras, allowing them to adapt slightly if a panel is marginally misaligned or a weld point needs micro-adjustment. In many production cells, Tesla has implemented what are known as friction stir welding units, robots capable of joining aluminum panels without melting them. This technique, originally developed for aerospace manufacturing, uses a high-speed rotating tool that generates frictional heat to soften and fuse materials without introducing impurities or thermal distortion. It results in stronger joints and is especially effective for joining thick battery pack casings or high-stress structural nodes. But Tesla's automation does not end at the mechanical level. Surrounding the physical robots is a vast, digital control infrastructure, powered by machine learning algorithms that analyze every torque value, weld voltage, and robot movement. These systems compare every single action against historical data to identify patterns that may indicate future faults. For example, if a particular welding arm shows a slight uptick in motion latency or current draw, the system can schedule predictive maintenance before a full failure occurs. This predictive maintenance loop dramatically increases uptime and reduces unexpected halts in the production line. Complementing this robotic workforce is a carefully integrated human team. Contrary to the misconception that gigafactories are purely robotic, Tesla maintains a robust human workforce in areas where judgment, dexterity, or problem solving are still superior to automation. For instance, interior trim installation, particularly tasks involving soft materials like Alcantara, stitched leather, or delicate wiring, still relies on trained technicians who can feel for correct tension, align materials by eye, and make subtle corrections during fitment. Human workers are also essential during final inspection, dynamic testing, and exception handling. If a part doesn't meet specifications, or if a software glitch prevents a subsystem from booting, it's often a human specialist who diagnoses and resolves the issue. These employees are equipped with digital tablets linked to Tesla's internal manufacturing cloud. They receive live data feeds from the vehicle's onboard sensors and can pull up schematics, tolerances, and previous production history in seconds. Every fix they apply, every note they enter, becomes part of that car's digital footprint, a log that follows it forever, even into post-sale diagnostics. Tesla's approach to worker efficiency is also shaped by ergonomic engineering and cognitive load optimization. Workstations are designed to reduce repetitive strain injuries with tool arms that balance heavy equipment and lift assists for placing components. Augmented reality overlays are sometimes used during training phases, projecting digital guides onto surfaces to help new employees understand complex assemblies. Rotational schedules ensure workers shift between physically demanding tasks and more routine duties, helping prevent fatigue-related errors. As we dig deeper into the brain of the Gigafactory, we arrive at what is perhaps Tesla's greatest long-term differentiator: the use of artificial intelligence, not just in the vehicles, but within the factory itself. Tesla doesn't merely automate individual machines, it trains its factories to optimize themselves. This is achieved through a combination of real-time data ingestion, cloud-based analytics, and reinforcement learning loops. Let's take an example from the paint shop. Traditionally, robots follow predefined spray paths based on CAD data. However, Tesla trains its painting robots using vision-based systems that analyze each body shell in real time for curvature, panel orientation, and gap uniformity. This data informs dynamic adjustments to spray trajectory, nozzle pressure, and stroke timing. The result is more uniform coating, fewer touch-ups, and improved long-term finish durability. Or consider battery pack assembly. Each cell inserted into a module is monitored for voltage, internal resistance, and capacitance. Tesla uses this data to build a profile of every module's thermal characteristics. If a pattern of abnormal cell degradation is observed in the field, engineers can trace it back to the exact production batch, process variables, or even environmental conditions at the time of assembly. This data loop enables retroactive improvements to manufacturing conditions and helps refine pack longevity models for future software updates. One of the more futuristic systems Tesla is rolling out across its newer gigafactories involves swarm intelligence for material transport. Rather than fixed conveyor systems, Tesla uses fleets of autonomous mobile robots that navigate the factory floor using SLAM algorithms. These robots aren't programmed with fixed paths. They learn optimal routes in real time, adapt to obstacles, and communicate with one another to avoid collisions or bottlenecks. This approach allows the factory layout to be more modular and reconfigurable, supporting agile production and faster adaptation to new models or variants. Equally fascinating is Tesla's use of simulation environments for factory operations. Entire sections of the Gigafactory are mirrored in a digital twin, an exact 3D replica of the physical space and its processes. Engineers can run simulations to test new workflows, evaluate machinery upgrades, or even plan how to integrate a new vehicle platform without ever disrupting the live production line. If a simulated robot collision is detected, the system can suggest path modifications or sequence changes before real-world implementation. This same philosophy extends to Tesla's use of custom silicon chips. While best known for its full self-driving computer, Tesla also designs specialized hardware for internal factory use. These include image recognition chips optimized for high-speed defect detection, edge computing units for data processing at the machine level, and embedded control systems that allow more precise energy regulation in welding and curing ovens. This level of hardware customization provides Tesla with granular control over quality, energy efficiency, and process speed. Another compelling layer of Tesla's factory evolution involves environmental engineering. Every Gigafactory is designed with sustainability as a core tenet. Rooftop solar arrays, on-site water recycling systems, and battery-powered internal logistics vehicles are just some of the components contributing to closed-loop manufacturing. The energy used to produce each Tesla vehicle is increasingly being sourced from renewable systems within the facility itself, dramatically lowering life-cycle carbon emissions. Tesla's focus on vertical integration again becomes critical here. When energy systems, battery chemistry, robotics, and software all originate from the same corporate ecosystem, coordination becomes exponentially easier. Design tweaks to the battery casing, for example, can immediately inform changes to the casting molds, welding fixtures, or software-based thermal models, without the friction of cross-company coordination. Perhaps the most emblematic symbol of this holistic integration is Tesla's gigacasting machines. These are among the most powerful aluminum die casting machines in the world, capable of creating entire underbody sections as a single solid piece. These machines, designed in partnership with Adidra, reduce the number of parts in the vehicle's chassis from hundreds to just a few, eliminating fasteners, reducing weight, and improving crash performance. Integrating such massive components into the production line requires not just physical reconfiguration, but software integration, supply chain alignment, and real-time QC adaptation, all of which Tesla is uniquely positioned to manage in-house. As we look at the sum of all these systems, robotics, AI, digital twins, human-machine interfaces, gigacasting, and energy-conscious infrastructure, it becomes clear that the Tesla production process is not simply a variation on traditional automotive manufacturing. It is an entirely new operating system for building cars. A platform, not just a plant. A fusion of machine intelligence, predictive analytics, physical innovation, and agile design thinking, all operating under a single cohesive philosophy. The Tesla Gigafactory isn't just where vehicles are built. It's where ideas are born, tested, scaled, and refined in real time. Where the boundary between hardware and software dissolves. Where every sensor, every weld, and every decision feeds back into a growing repository of knowledge that powers the next generation of vehicles, robots, factories, and systems. One of the most disruptive engineering breakthroughs in Tesla's modern manufacturing playbook is the integration of the structural battery pack, a complete rethinking of how the battery, chassis, and underbody of the vehicle work together. In traditional automotive design, the battery pack is a standalone component, an energy container bolted to the car's underbody. But in Tesla's structural pack architecture, pioneered with the 4680 battery format, the battery no longer rides beneath the structure, it becomes the structure. To understand the scale of this shift, we first need to explore the 4680 cell itself. Named for its dimensions, 46mm wide and 80mm tall, the 4680 cylindrical lithium-ion cell represents a significant departure from the older 2170 and 18650 formats. It offers 5 times the energy, 6 times the power, and reduces the cost per kilowatt hour significantly. But it's not just the size that matters, it's how the cells are built and what they enable downstream in manufacturing. Each 4680 cell is designed to support tabless internal architecture. In conventional cells, current must travel through a tab, a narrow conductor that can create resistance and heat. In Tesla's tabless design, the entire edge of the rolled electrode acts as a current collector, enabling more uniform heat distribution and higher current throughput. This drastically reduces internal resistance, improves efficiency during charge and discharge, and simplifies thermal management, a critical benefit when assembling high-density battery modules. These cells are produced in a vertically integrated line that starts with electrode slurry mixing, followed by coating, calendaring, cutting, and winding, all performed under strict environmental control. The wound jelly rolls are inserted into steel canisters, filled with electrolyte, sealed by laser welding, and then aged, tested, and sorted. What's remarkable is that Tesla's battery lines are not just production machines, they are learning machines. Each stage of battery cell production is heavily instrumented, with sensors that track viscosity, coating uniformity, line tension, and thermal behavior. These metrics feed back into AI-driven quality control systems that adapt in real time, reducing scrap rates and improving yield without requiring line shutdowns. Once the cells are complete, they are no longer assembled into modules as in traditional EVs. Instead, Tesla places them directly into the structural battery pack housing, eliminating intermediary module structures. This pack is a part of the vehicle's load-bearing frame, not an add-on. The cells are bonded in place using structural epoxy, and this bonded matrix provides rigidity akin to an aircraft's wing box design, a technique borrowed from aerospace engineering. A critical enabler of this approach is the use of high-performance structural foams and thermal adhesives. These materials serve multiple functions simultaneously. They manage vibration and noise, conduct heat away from the cells to integrated cooling loops, and crucially, form part of the vehicle's crash energy management system. During side or front impacts, the structural battery pack helps distribute forces across a wider area, reducing localized deformation and improving occupant safety. In the Gigafactory, structural pack assembly is a distinct line, physically separate from standard battery operations due to its unique tooling requirements. Cells are loaded into the pack casing using high-speed robotic insertion machines. Adhesive dispensing systems apply precisely metered quantities of 2-part epoxy at high pressure. Once cells are in place, the entire structure is cured in massive industrial ovens that bring the adhesive to full mechanical strength. After cooling, the pack undergoes precision machining to create interfaces for the drive unit, seat mounts, and body attachment points. What results is not just a battery, it's a central element of the vehicle's physical frame. The top of the pack often serves as the interior floor of the cabin. The bottom, reinforced by ribbed aluminum or composite materials, acts as the underbody and aerodynamic tray. By combining energy storage, structural support, and crash safety into a single unit, Tesla eliminates dozens of separate components, reducing mass, simplifying manufacturing, and slashing costs. Now, integrate this with another innovation, gigacasting. Tesla's use of giant aluminum die-casting machines to form the front and rear underbody sections of its vehicles is nothing short of revolutionary. These Idura Giga Press machines, weighing over 400 tons and applying clamping forces in the range of 6,000 to 9,000 tons, can create entire frame sections as a single cast. Instead of welding together hundreds of stamped components, Tesla now forms massive structural elements in one shot, lighter, stiffer, and far faster to produce. When the front and rear castings are combined with the central structural battery pack, Tesla essentially builds the entire underbody of a vehicle using just 3 large parts. These unibody trios replace what was once over 300 parts in older chassis architectures. This not only reduces complexity and assembly time, but also minimizes the number of suppliers, welds, fixtures, and potential quality defects. Each casting is inspected via X-ray and ultrasonic imaging to detect porosity, cracks, or incomplete fills. Any anomalies are rejected and remelted, maintaining a closed-loop aluminum recycling system. This radical simplification also redefines how the rest of the car is built. Traditional automotive factories are organized around a highly linear body-in-white process: frame construction, then floor pan, then underbody integration. Tesla's method is more like assembling a modular aircraft, where large sub-assemblies are brought together at fewer, more tightly controlled junctions. This allows Tesla to create more compact factories with faster cycle times and fewer workers per unit produced, metrics that directly impact capital efficiency and return on investment. To support these next-generation designs, Tesla continues to invest heavily in materials science research, much of it focused on high-strength aluminum alloys, advanced polymers, and die-casting feedstock refinement. The development of proprietary aluminum alloys that combine excellent flow characteristics in casting with high tensile strength post-treatment is a crucial part of making gigacasting work. These alloys must cool evenly, avoid brittleness, and withstand both crash loads and environmental exposure over time. In parallel, Tesla is exploring dry electrode manufacturing for future battery lines, a technique that eliminates the solvent-heavy coating and drying stages currently used in electrode production. Dry electrodes can be applied directly to the current collector using pressure and heat, significantly reducing energy consumption, production footprint, and cost. This aligns with Tesla's vision for more sustainable, vertically integrated gigafactories, ones that consume fewer resources per gigawatt hour and can be rapidly scaled in new geographies. Indeed, Tesla's goal is not just to build more cars, it's to scale manufacturing like a technology company, not an industrial one. This means shorter ramp-up times, smaller capital expenditures per unit of output, and a globally unified software-hardware stack that can be deployed anywhere in the world with minimal localization. Future gigafactories, like those planned in Mexico and India, are being designed with these structural pack and casting concepts at their core, meaning they won't just produce the next generation of Tesla vehicles, they will be born already optimized for speed, simplicity, and flexibility. This systems thinking extends even further into factory floor layout and material flow logistics. With fewer total parts, Tesla can implement straighter, more continuous material pathways, reducing the need for kitting, buffering, and material staging. Instead of having dozens of sub-assembly lines feeding hundreds of components, Tesla can deliver entire modules, like castings or packs, straight to the marriage station, where the vehicle begins to take its final form. This layout change reduces floor space, lowers error rates, and improves throughput. It also allows for greater software simulation of factory dynamics. When each vehicle only passes through 30 or 40 production cells, rather than 200 or 300, it becomes computationally feasible to simulate the entire factory in real time. AI-based systems can then test flow changes, balance labor loads, and reroute production if a bottleneck emerges, all before any change is implemented on the floor. The result is a self-learning, self-optimizing factory capable of adapting to demand shifts, supplier disruptions, or design updates faster than legacy automakers can retool a single line. All of this innovation, structural batteries, 4,680 cells, gigacasting and software-first factories converges into a clear strategic objective: build more cars, better and faster, with fewer people and lower capital costs per unit. It's not about squeezing the last drop of efficiency from legacy systems. It's about replacing those systems entirely. And the boldness of that approach is why Tesla's manufacturing story remains one of the most closely watched industrial transformations of the 21st century. The journey starts in Chevrolet's design and engineering departments, where teams of designers, mechanical engineers, and manufacturing planners work together to create not just the look of a vehicle, but the exact way it will be built. The earlier stages are dominated by design feasibility. Engineers ensure that the proposed vehicle shapes, curves, and mechanical layouts are compatible with large-scale manufacturing techniques. This includes determining how each body panel will be stamped, how wiring harnesses will be routed, and how components will be positioned for both performance and serviceability. It is here that design for assembly comes into play. In every element must be optimized for efficient installation without compromising quality or safety. This is especially critical for Chevrolet, which produces a wide range of models, from compact sedans to full-size trucks, each with very different manufacturing needs. Once the design is finalized, manufacturing engineering takes the blueprint and transforms it into a step-by-step factory plan. This involves defining which machines, robots, and tooling will be used at each stage of production, how workers will interact with them, and how the line will be sequenced to handle multiple model variations. Many Chevrolet plants are designed for mixed model production, meaning that a pickup truck and a crossover SUV could be assembled back-to-back on the same line. This requires extremely precise scheduling and tooling flexibility. The process begins with raw material arrival, particularly steel and aluminum sheets that form the vehicle's structural backbone. These materials arrive at the stamping plant in the form of enormous coils, each weighing many tons. The coils are unrolled, cut into blanks, and fed into massive stamping presses. These presses, some of the largest machines in the automotive world, shape the metal into fenders, roofs, doors, and other body panels using dies that weigh several tons themselves. Each panel typically goes through several stamping stages, moving from a rough shape to precise final contours. During stamping, dimensional accuracy is paramount. Even a fraction of a millimeter of error can cause alignment issues later in the build. Chevrolet uses automated inspection systems to verify each panel's geometry, rejecting or recycling any piece that fails to meet exact standards. This quality control in the stamping phase prevents costly rework later down the line. From stamping, the panels move into the body shop. Here, the flat, separate pieces are joined together to form the body in white, the term for the bare, unpainted vehicle shell. This process is dominated by robotic spot welding, where arms with welding guns move in perfectly choreographed sequences to fuse the panels together. The body shop operates on a combination of fixtures and jigs that hold each piece in precise alignment, ensuring structural strength and proper fit. The floor pan is laid down first, then side panels, roof structures, and reinforcements are added in a sequence determined by both structural integrity and manufacturing efficiency. Chevrolet plants use hundreds of welding robots, but human oversight remains critical. Skilled technicians monitor the welding cells, handle complex welds in tight spaces, and conduct random sample checks to confirm that weld penetration and positioning meet specifications. In some areas, adhesive bonding is used alongside welding to increase rigidity and reduce noise, vibration, and harshness. After the body is fully assembled, It undergoes detailed dimensional checks using coordinate measuring machines or laser scanning systems. If all is within tolerance, the body in white moves to the paint shop. The paint process is one of the most controlled environments in the factory, as even a speck of dust can mar the finish. The first step in painting is cleaning and pre-treatment. The body is submerged in a series of chemical baths to remove grease, oils, and contaminants. A phosphate coating is then applied to improve corrosion resistance. This is followed by the electrophoretic deposition, or E-coat, where the body is dipped in a charged primer bath that ensures complete coverage in every nook and cavity. The E-coat is then baked to cure it into a durable base layer. Once primed, the body passes through sanding and inspection areas before moving to the color base coat booths. Chevrolet's paint lines often use robotic spray arms programmed to follow complex paths that ensure an even application over curves, edges, and recessed areas. Some vehicles receive two-tone paint or special finishes, requiring masking and multiple spray cycles. The base coat is followed by a clear coat, which provides gloss and protection from UV rays and environmental wear. Each coat is baked in ovens to cure it, hardening the finish for durability. After the final paint cure, the body emerges looking complete on the outside, but it is still just a shell with no functional systems. This is where the trim and chassis assembly phases begin. The painted bodies move onto the trim line, where workers and robots install interior components in a carefully sequenced order. Wiring harnesses are routed through the body, HVAC ducting is fitted, and dashboards are installed as complete units. Seats, carpets, door panels, and center consoles are added, with quality checks at each station. Parallel to this, in another part of the plant, chassis sub-assemblies are being prepared. Engines, transmissions, front and rear suspension units, exhaust systems, and brake assemblies are mounted onto subframes. This pre-assembly ensures that when the time comes, the drivetrain can be installed into the body quickly and accurately. With the major mechanical and trim installations complete, the Chevrolet moves into the final assembly verification and testing phase. At this point, the vehicle is fully recognizable, but its systems have yet to prove themselves under controlled evaluation. This stage is where the factory shifts its focus from building to validating. One of the first stops is the wheel alignment station. Using laser-based or camera-guided systems, technicians check the alignment angles for each wheel: camber, caster, and toe. Proper alignment is essential not only for safe handling, but also for tire longevity and fuel efficiency. Adjustments are made at the suspension components until all readings are within Chevrolet's specified tolerances. These specifications are tied to each model's unique suspension geometry, ensuring consistent road feel across every unit. Next, the vehicle proceeds to the fluid fill and system pressurization stage. While many fluids, such as engine oil, brake fluid, and coolant have been partially filled earlier in the assembly process, this step ensures that all are topped off to exact levels and that the systems are free of leaks or trapped air. For braking systems, pressure testing and bleeding are performed to guarantee firm pedal feel and consistent stopping power. The fuel system is also pressurized and checked for leaks, as even minor seepage can create both safety and emissions compliance issues. Then comes one of the most exciting moments on the factory floor: the first engine start. At a dedicated startup station, the technician engages the ignition, bringing the Chevrolet's powertrain to life for the very first time. The engine's idle is monitored closely for smoothness, proper fuel-air mixture, and the absence of unusual noises or vibrations. The onboard diagnostic system is immediately scanned to ensure no fault codes are present. If a code does appear, it is addressed on the spot before the car moves on. After the initial start, the vehicle advances to the rolling road test, also known as the dynamometer station. Here, the car's drive wheels rest on large rollers that simulate real road resistance. A trained operator runs the vehicle through different speed ranges, gear changes, and acceleration profiles, while onboard sensors monitor performance. For automatic transmissions, shift smoothness is evaluated. For manual transmissions, clutch engagement and gear selection are tested. Braking performance is also checked under controlled simulated loads. This phase helps confirm that the powertrain, drivetrain, and braking systems are functioning exactly as intended before the vehicle ever touches pavement outside the plant. Following the rolling road, the vehicle undergoes an emissions and noise compliance check. In the emissions booth, exhaust gases are captured and analyzed by high-precision equipment to ensure they meet the regulatory standards of the destination market. For noise compliance, sound level meters measure exterior and sometimes interior noise levels under specified conditions, ensuring that they fall within acceptable limits for both legal compliance and customer comfort. With these mechanical verifications complete, attention shifts to fine detailing and final adjustments. At the fit and finish inspection stations, experienced workers examine every panel gap, every seam, and every interior surface for perfection. Door alignment, hood closure effort, and trunk latch operation are all tested. Inside the cabin, all switches, controls, lighting, and infotainment functions are checked one by one. Even the alignment of stitching on seat upholstery can be grounds for rework if it fails to meet the brand's aesthetic standards. One of the more dramatic quality checks is the water leak test. The Chevrolet is driven into a sealed booth equipped with high-pressure spray nozzles that douse the vehicle from all directions, simulating heavy rainfall and road spray conditions. After several minutes, the vehicle is opened and inspected for any trace of water inside. Any leak, no matter how minor, is immediately repaired, often by replacing seals or adjusting window or door fitment. Once the car passes the water test, it proceeds to the underbody inspection area. Here, the vehicle is lifted and technicians check for proper routing of hoses, cables, and exhaust components. Protective coatings are examined to ensure full coverage, especially in corrosion-prone areas such as wheel wells and chassis rails. This stage is also a final safeguard for identifying loose fasteners or missing clips. The last stage before leaving the assembly building is the final audit. This is a comprehensive evaluation combining visual, functional, and performance checks into one ultimate sign-off process. The audit team often includes some of the most experienced personnel in the plant, and their approval is a requirement before a car can be released. Every system, from headlights to climate control, is tested again, and any deviation from perfect operation is corrected immediately. Once signed off, the Chevrolet is prepared for shipment. Protective plastic films are applied to painted surfaces most vulnerable to transit damage, such as hoods, roofs, and door edges. The interior is covered with disposable mats, seat covers, and steering wheel wraps to keep it pristine until delivery. From here, the vehicle enters the shipping yard, where it is grouped with others bound for the same distribution points. Domestic-bound vehicles are loaded onto specialized car carrier trucks with wheel straps securing them in place. For longer domestic routes, some are shipped by rail in enclosed auto racks. Export vehicles are driven onto roll-on/roll-off ships for overseas transport, where they are secured in dense, organized rows for the voyage. Upon arrival at regional distribution centers or directly at dealerships, each Chevrolet undergoes a pre-delivery inspection to ensure that transport has not caused any damage or alignment issues. Fluids and tire pressures are rechecked and protective coverings are removed. If accessories ordered by the customer were not installed at the factory, they may be fitted at this stage. Only after this chain of precise manufacturing, rigorous testing, and careful transport does the vehicle reach the customer. From the initial design to the moment the keys are handed over, every Chevrolet is the product of thousands of coordinated actions each performed to uphold the brand's standards of reliability, performance, and quality. Long before a Hyundai rolls out of a showroom or cruises down a highway, it begins life in a complex and highly synchronized industrial process that blends advanced automation with skilled human craftsmanship. The journey starts far from the factory floor, in Hyundai's design and engineering centers, where teams of stylists, mechanical engineers, safety experts, and manufacturing specialists collaborate to transform a concept into a buildable reality. This early collaboration is critical. It ensures that the car's shape, structure, and systems are not only aesthetically pleasing and mechanically sound, but also feasible to mass produce. Every curve of the body is analyzed for how it will be stamped from metal sheets. Every bracket and mounting point is evaluated for efficient installation, and every wiring harness route is mapped to avoid interference with other systems. Hyundai applies design for manufacture principles from the outset, reducing assembly complexity and ensuring consistent quality. Once the design is finalized, the manufacturing engineering teams take over. Their task is to translate that design into a precise, step-by-step production plan that integrates seamlessly into Hyundai's global manufacturing network. This means specifying which machines, robotic systems, and fixtures will be required, how the assembly line will be arranged, and what level of automation each task demands. Many Hyundai plants are set up for mixed model production, allowing sedans, SUVs, and even electric vehicles to be built on the same line. This flexibility demands exceptionally detailed scheduling and tooling strategies. The process physically begins with the arrival of raw materials. The backbone of most Hyundai vehicles is steel, often high strength, and sometimes blended with lightweight aluminum alloys for weight savings. These materials arrive in the form of massive coils, each weighing several tons, delivered by rail or truck directly to the stamping plant. Before the first press stroke, these coils are unrolled, cut into flat blanks, and fed into enormous stamping presses. These presses are monumental machines capable of exerting thousands of tons of force. They shape the flat metal sheets into body panels, such as fenders, roof sections, hoods, and door skins. Each panel typically passes through a series of dies, the first forming a rough shape, the following ones refining it to exact tolerances. Hyundai's dies are precision engineered and often swapped out by automated die changing systems to minimize downtime between production runs. Dimensional accuracy at this stage is essential. Even a slight misalignment in a stamped panel can cause compounding fitment problems later. To prevent this, Hyundai employs automated vision systems and laser scanners that inspect each panel as it leaves the press. Any panel outside specification is sent for recycling, with the metal returned to the supply chain to minimize waste. From stamping, the panels move into the body shop, a vast, robot-dominated hall where the skeletal structure of the car is assembled. Here, the flat pieces are transformed into the three-dimensional form of the vehicle in a process known as body-in-white assembly. This stage is dominated by robotic spot welding, with articulated arms, moving in carefully choreographed sequences to fuse panels together at hundreds of points. The process starts with the floor pan, onto which side frames, roof rails, and bulkheads are positioned and clamped into place by large jigs. These jigs ensure precise alignment so that every vehicle matches the dimensional blueprint exactly. Additional reinforcements are added at structural stress points, such as the pillars between the doors and the crash-absorbing sections at the front and rear. Although robots do the majority of welding, skilled human operators remain essential in the body shop. They handle welds in areas where robotic arms cannot easily reach, inspect the quality of robotic welds, and make fine adjustments to ensure panel gaps and alignment stay within tolerances. In some Hyundai models, structural adhesives are applied alongside welds to increase rigidity and reduce noise, vibration, and harshness in the finished car. Once the body shell is fully welded, it undergoes a dimensional inspection. This involves laser measurement systems or coordinate measuring machines that scan key reference points to ensure that the body conforms to the exact design specifications. Any deviation, even as small as a millimeter, can lead to problems fitting doors, glass, or interior components later. When the body passes inspection, it proceeds to the paint shop, one of the most meticulously controlled environments in the entire factory. The paint process is highly sensitive to dust, humidity, and temperature, so the paint shop is sealed and climate controlled. Before painting begins, the body is cleaned and pre-treated in a series of immersion baths. These remove oils from stamping and welding, apply a corrosion-resistant phosphate layer, and prepare the surface for primer adhesion. Following pre-treatment, the body is submerged in an electrically charged primer bath in a process called electrophoretic deposition, or e-coating. This ensures that primer reaches even hidden cavities, providing a uniform anti-corrosion layer. The body is then baked in an oven to cure the coating into a hard, protective shell. Next comes surface preparation. Technicians and automated sanding units smooth the primed surface, removing any tiny imperfections. The body then enters the base coat booths, where robotic arms apply the vehicle's chosen color in ultra-fine, even layers. For certain models, multi-coat or two-tone paint schemes require masking and additional spray cycles. After the base coat, a clear coat is applied to give gloss and long-term UV and chemical resistance. Each coating layer is cured in a controlled temperature oven to ensure hardness and durability. When the body emerges from the paint shop, it looks like a complete vehicle from the outside, but it is still just a shell. No drivetrain, no interior, and no wiring. This is when it moves to the trim and chassis assembly areas, where it truly begins to take on life. The first steps in trim assembly involve installing insulation and wiring. Sheets of sound-deadening material are placed strategically in the floor, doors, and bulkhead areas to reduce road and engine noise. Pre-assembled wiring harnesses are then routed through the vehicle, connecting future components such as lights, sensors, the infotainment system, and power accessories. These harnesses are secured with clips and ties to prevent rattles and wear over years of use. While the wiring is being installed, HVAC ducting and other hidden systems are fitted. Then comes the dashboard, which often arrives as a complete module from a supplier. Installing the dash is a delicate process, requiring alignment with mounting points and simultaneous connection of numerous wiring plugs. After the dashboard, seats are installed, bolted into the floor, and connected to their respective power or heating controls if equipped. Meanwhile, in a separate section of the plant, chassis and drivetrain components are being assembled into a single underbody module. This includes the engine, transmission, front and rear suspension units, exhaust system, and sometimes the steering assembly. Hyundai uses modular assembly techniques so that this entire unit can be brought to the body in one coordinated step. That step is known as the marriage, and it is one of the most visually striking moments on the assembly line. The painted body shell is suspended slightly above the moving chassis unit, and then the two are lowered and joined together. Bolts are torqued to precise specifications, linking the engine, drivetrain, and suspension to the body. Once the marriage is complete, fluid lines, electrical connections, and control linkages are secured between the body and chassis. This is followed by glazing, installing the front and rear windshields and side windows. High-strength adhesives bond the glass to the frame, contributing to both structural rigidity and weather sealing. By this stage, the Hyundai is a complete, self-contained unit, but it must undergo rigorous testing adjustment, and final detailing before it is ready to leave the factory. With the body and chassis joined and the major mechanical systems in place, the Hyundai enters the final stages of production. A series of detailed inspections, dynamic tests, and finishing touches that ensure it meets both regulatory standards and Hyundai's own quality benchmarks. This part of the process is just as critical as stamping or welding because it determines whether the car will leave the factory flawless or require rework. The first stop is often the wheel alignment station. Using laser-guided or camera-based systems, technicians check the vehicle's suspension geometry, ensuring that the camber, caster, and toe of each wheel match precise factory specifications. Proper alignment not only affects handling and stability, but also determines tire wear and fuel efficiency. Adjustments are made by trained workers using specialized tools, often within a tolerance of a fraction of a degree. From alignment, the vehicle moves to fluid fill and system pressurization. Even though some fluids, such as engine oil or coolant, may have been partially filled earlier in the assembly, this stage ensures all systems are topped to exact levels. The brake and clutch systems are bled of any trapped air, guaranteeing consistent pedal feel. The air conditioning system is charged with refrigerant, and the fuel system is pressurized to check for leaks. In hybrid or electric models, the high voltage battery systems are also energized and checked for correct function. One of the most significant milestones comes next: the first engine start. At a dedicated station, a technician initiates the ignition sequence or engages the start button. The powertrain roars or hums to life for the very first time. While this moment has a certain ceremonial feel, it is primarily a diagnostic test. Sensors and the onboard diagnostic system are immediately scanned for error codes, while technicians listen for any abnormal sounds and monitor idle stability. Any fault detected is addressed immediately before the car progresses. Following the initial start, the Hyundai is driven onto a rolling road dynamometer, a sophisticated test rig with large rollers beneath the wheels. Here, the vehicle's drivetrain is run through a series of simulated driving conditions. Technicians shift through gears, accelerate, decelerate, and brake, all while sensors record performance metrics. This test checks everything from transmission shift quality to ABS functionality. For electric and hybrid vehicles, regenerative braking performance is also verified. The dynamometer can simulate different road loads, allowing Hyundai to ensure the vehicle responds correctly in both light and heavy driving scenarios. Next, the vehicle enters an emissions and noise compliance station. The exhaust system is connected to high-precision analyzers that measure levels of pollutants such as carbon monoxide, hydrocarbons, and nitrogen oxides, ensuring compliance with the environmental regulations of the target market. Noise testing is also performed, measuring sound levels both outside and sometimes inside the cabin to confirm they meet legal and brand comfort standards. Once mechanical and emissions checks are complete, the Hyundai proceeds to the fit and finish inspection area. This is a zone where highly trained quality inspectors meticulously examine the car's exterior and interior for even the smallest imperfections. Panel gaps are measured with gauges, paint surfaces are inspected under bright, angled lighting to reveal any blemishes, and all interior features are tested for correct operation. If a trim piece is misaligned by even a millimeter, it is corrected on the spot. One of the most important tests at this stage is the water leak test. The car is driven into a sealed chamber fitted with high-pressure spray nozzles, which bombard it with water from all angles to simulate heavy rainfall and road spray. After several minutes, technicians open the doors, trunk, and hood to inspect for any signs of moisture inside. Leaks are unacceptable, so any that are found trigger immediate sealing repairs or component adjustments. Underbody inspection follows, with the vehicle lifted on a hoist so workers can check that exhaust systems, fuel lines, brake hoses, and electrical cables are correctly routed and securely fastened. Protective coatings applied earlier in the build are examined for complete coverage, especially in high corrosion areas like wheel wells and chassis cross members. The final audit is the last checkpoint before a Hyundai can be cleared for shipment. This audit is a condensed but highly rigorous version of all prior tests. Inspectors cycle through every electrical control, verify all lighting and warning systems, and ensure the climate control works in heating and cooling modes. They also test locking systems, window regulators, mirrors, infotainment units, and safety features like airbags through diagnostic systems. The goal is to confirm that the car leaving the factory is indistinguishable in quality from any other unit of the same model, regardless of production date. Once the final audit is passed, the car moves to the shipping preparation area. Protective films are applied to vulnerable painted surfaces, such as the hood, roof, and trunk lid, to guard against minor scratches or debris during transport. Interior surfaces, such as seats and steering wheels, are wrapped with disposable covers. The vehicles are then driven to the factory's dispatch yard, a vast parking area organized by destination. Here, they are scanned into Hyundai's logistics system using their unique vehicle identification numbers. This tracking system links each car to its market, dealer, and production details. Domestic shipments are typically loaded onto multi-deck car carrier trucks, secured with wheel straps to prevent movement. For longer domestic journeys, rail transport in enclosed auto racks may be used. Vehicles bound for export markets are moved to ports, where they are driven onto roll-on/roll-off ships. These massive vessels function like floating parking garages, with cars parked in tight formation and secured for the ocean voyage. Once at their destination country, the vehicles undergo customs clearance before heading to Hyundai's regional distribution centers. Here, a process called pre-delivery inspection, or PDI, is performed. This includes removing protective coverings, checking fluid levels and tire pressures, and confirming no damage occurred during transport. Any market-specific adjustments, such as headlight alignment or software settings, are made at this stage. From the distribution center, the cars are delivered to dealerships, where a final light inspection is carried out before they are placed on display or prepared for customer delivery. When the new owner takes the keys, the journey that began with raw steel coils and a concept drawing is complete. Though for Hyundai, the feedback loop from customer to factory continues, helping refine the next generation of vehicles. Before a Nissan vehicle ever reaches the open road, its story begins long before the first bolt is tightened or the first panel is painted. The creation of a Nissan car is a journey that blends advanced engineering, precision manufacturing, and human skill into a seamless, highly coordinated process. It begins in design studios and engineering departments, where the model is conceived, refined, and optimized for production. Design is never just about looks. For Nissan, every curve and contour is evaluated for aerodynamic efficiency, structural integrity, and manufacturability. Engineers work closely with manufacturing planners to ensure that the design can be built consistently at high volume. This process is called design for manufacturability, and it addresses questions like, can a panel be stamped without deforming? Can a wiring harness be installed without excessive labor time? Can a structural weld be made easily by a robot? These early decisions will determine the efficiency and quality of the factory floor operations months or even years later. Once the design is finalized, manufacturing engineering takes over. This is where the factory plan is built, specifying the sequence of operations, the type of machinery to be used, and the layout of the assembly line. Nissan's factories are often capable of building multiple models on the same line, which means the plan must account for mixed model production. In practice, this requires flexible tooling, quick change robotic programs, and precisely timed deliveries of parts so that the right components are always at the right station when a specific model arrives. The physical process starts with the arrival of raw materials, primarily steel and aluminum. These materials, often in the form of giant coils weighing several tons, are delivered by rail or truck to the plant's stamping facility. Before a single press stroke is made, the coils are unrolled, flattened, and cut into blanks, flat sheets of the correct size for the parts to be made. These blanks are then fed into huge stamping presses capable of exerting thousands of tons of force. Each body panel, whether it's a door skin, roof panel, fender, or hood, is formed by passing through several stages of dies. The first die forms the rough shape, while subsequent dies refine the panel, adding curves, ridges, and precise dimensions. The dies themselves are precision-engineered steel blocks that must be perfectly aligned and maintained to avoid defects. Quality checks start here. Robotic measuring arms or laser scanners inspect the panels for dimensional accuracy and surface quality. Even minor ripples or distortions can cause problems later during assembly, so any out-of-spec panels are removed from the line and sent for recycling. From stamping, the panels are moved into the body shop, a large, highly automated hall where the panels are welded together to form what is known as the body in white. This is the skeletal shell of the car before painting and assembly. Large jigs and fixtures hold panels in the exact position while robotic arms perform spot welds, fusing the metal together. In modern Nissan plants, robots handle the majority of welds, ensuring speed, repeatability, and strength. The process usually starts with the floor pan. Side panels, roof structures, and cross members are added in a carefully planned sequence to maximize rigidity and precision. Reinforcements for crash safety, such as high-strength steel beams in the doors and roof pillars, are installed at this stage. Doors may be temporarily hung for alignment checks, but are often removed later to make interior assembly easier. Although automation dominates, human workers remain essential. Some welds, especially in tight or complex areas, are better handled by skilled technicians. Workers also monitor the robotic systems, making adjustments when necessary and performing visual checks for weld integrity. When the body shell is complete, it undergoes a dimensional inspection using coordinate measuring machines or laser scanning systems. This ensures that the structure matches the precise dimensions required for later assembly steps, where mismatches can cause issues with panel fit or sealing. Next, the bare metal body heads to the paint shop, an area of the factory with the most stringent cleanliness requirements. Dust, dirt, and moisture can ruin a finish, so the paint shop is a sealed, climate-controlled environment. Before painting, the body goes through a series of pre-treatment baths to remove any residual oil or dirt from stamping and welding. These baths also apply a phosphate layer that improves corrosion resistance. After pre-treatment, the body undergoes electrophoretic deposition, or e-coating. In this process, the body is submerged in a primer bath where an electric charge causes the primer particles to bond evenly to the entire surface, including hidden cavities and seams. The coated body is then baked in an oven to cure the primer into a hard, protective layer. Once cured, the body is sanded to smooth the surface before the color coats are applied. Robotic sprayers, precisely programmed for each model and color, apply the base coat evenly over every contour. In some cases, human painters handle special finishes or complex two-tone applications. After the base coat, a clear coat is applied to provide gloss and protect against UV and environmental damage. Each coat is cured in an oven, hardening the finish and locking in the color. When the painted body emerges, it looks complete on the outside, but remains an empty shell. The next stage, trim and chassis assembly, is where the car starts to take shape as a functional vehicle. The first step in trim is installing sound-deadening materials, insulation, and wiring harnesses. These harnesses, pre-assembled into model-specific layouts, are routed through the body and secured in place. HVAC ducting is fitted, followed by the dashboard, which usually arrives as a fully assembled unit from a supplier. Seats are bolted into place, carpet is laid, and door panels are installed. In parallel, the plant's chassis line is assembling the mechanical heart of the car. The engine, transmission, suspension assemblies, exhaust system, and brakes are mounted onto a subframe or separate underbody unit. This modular approach allows for rapid final assembly once the chassis and body are ready to be joined. The marriage process is one of the most striking moments in Nissan's assembly line. The painted body is suspended above the rolling chassis module, and the two are brought together by synchronized lifts. Bolts are torqued to specification, connecting the drivetrain and suspension to the body. Following the marriage, technicians connect the various systems between body and chassis, electrical plugs, coolant hoses, fuel lines, steering linkages, and more. Windows are installed using high-strength adhesive, and exterior trim pieces such as weather strips, moldings, and badges are applied. At this point, the Nissan is a complete vehicle in form, but must still prove itself in function. The next phase, testing, inspection, and final adjustments, will determine whether it is ready for shipment to customers. With the major assembly work finished and the Nissan now standing as a complete vehicle, the factory's focus shifts toward verification, fine-tuning, and preparing it for the journey beyond the plant gates. This stage is not simply a final glance over the product. It is a comprehensive series of tests and inspections designed to ensure that every function operates exactly as intended and that the vehicle meets Nissan's rigorous quality standards as well as the legal requirements of its destination market. The first stop in this phase is usually the wheel alignment station. Here, precision laser or camera-based measurement systems determine the exact angles of each wheel relative to the chassis. Technicians adjust camber, caster, and toe to within factory specifications. A misalignment at this stage would not only affect handling and tire life, but could also cause warranty claims, so the process is handled with meticulous care. From there, the vehicle moves to the fluid fill and pressurization stage. While some fluids such as oil and coolant may have been partially filled earlier, this step ensures that all systems are fully charged to their specified capacities. Brake and clutch hydraulics are bled to remove any trapped air, guaranteeing a firm pedal feel. Air conditioning systems are charged with refrigerant, the fuel system is primed, and in hybrid or electric models, high-voltage battery systems are energized and checked for correct operation. Each fill station uses automated metering systems to deliver exact volumes, minimizing waste and ensuring repeatability. One of the most anticipated moments comes next, the first engine start. At a dedicated station, the technician engages the ignition or push-button start, bringing the Nissan's powertrain to life for the very first time. While this might appear ceremonial, it is primarily a diagnostic event. The vehicle's onboard computer is scanned for any fault codes, idle speed is observed, and technicians listen closely for any unusual noises or vibrations. If a warning light appears or a diagnostic scan reveals an error, the vehicle is diverted to a repair bay before continuing. Once the initial startup checks are complete, the Nissan moves to the rolling road, also called the chassis dynamometer. Here, the drive wheels rest on large rollers that simulate road resistance. A trained operator runs the vehicle through various speeds, load conditions, and gear changes, while onboard sensors and external instruments record performance. This stage verifies smooth transmission shifts, proper acceleration response, correct ABS function, and stability control operation. For electric and hybrid models, regenerative braking efficiency is also tested. Following the dynamic test, the vehicle enters the emissions and noise measurement booth. Exhaust gases are captured and analyzed to ensure compliance with the emissions regulations of the market the car is destined for, whether that's Europe, North America, or Asia. The booth may also include sound level monitoring to verify that engine and exhaust noise remain within acceptable limits. For some models, interior noise levels are also measured to maintain Nissan's comfort standards. With the drivetrain and emissions verified, the Nissan proceeds to the fit and finish inspection zone. This is a brightly lit area where experienced inspectors examine every exterior panel and interior surface. Panel gaps are measured to ensure uniformity, and paint is checked under angled lighting that reveals imperfections invisible in normal conditions. Inside, every control, switch, and display is operated to confirm proper function. HVAC systems are tested for both heating and cooling performance, infotainment units are powered on, and tested for audio quality, and safety features, such as seatbelt warning systems, are checked. One of the most critical functional tests is the water leak check. The car is driven into a sealed chamber fitted with high-pressure water nozzles that bombard it from all directions, simulating heavy rain or car wash conditions. After several minutes of soaking, technicians enter the vehicle to check for even the slightest signs of moisture. Any leak detected, whether from a window seal, door gasket, or body seam, results in immediate repair and retesting. Next comes the underbody inspection. The vehicle is lifted on a hoist so workers can examine fuel lines, brake hoses, exhaust components, and electrical wiring for correct routing and secure fastening. Protective coatings applied earlier in the build are checked to ensure they fully cover vulnerable areas, especially in regions prone to corrosion. This step also allows for one last visual confirmation that no tools, fasteners, or foreign objects have been left behind during assembly. The last in-plant checkpoint is the final audit. This is a comprehensive, multi-point inspection that serves as the ultimate quality gate before the vehicle is released for shipping. The audit team includes some of the most experienced inspectors in the plant, and their role is to verify that every system operates flawlessly. The process includes both static checks, such as lights, controls, and displays, and short, low-speed driving within the factory grounds to confirm steering feel, brake performance, and noise levels. When a Nissan passes the final audit, it is cleared for shipment. In the shipping preparation area, protective films are applied to painted surfaces most likely to be scuffed during transport, such as the hood, roof, and door edges. Interior surfaces like the seats, steering wheel, and carpets are wrapped with disposable covers. The cars are then driven to the factory's dispatch yard, where they are parked in organized rows according to their destination. Each vehicle is scanned into Nissan's logistics system using its unique vehicle identification number, linking it to production data, quality records, and shipping instructions. Domestic-bound cars are usually loaded onto multi-level car carrier trucks, with each vehicle secured using wheel straps or chocks to prevent movement. For longer inland journeys, rail transport in enclosed auto racks is sometimes used. Export vehicles are driven onto roll-on/roll-off ships, enormous vessels designed specifically for transporting thousands of cars at once. Inside the ship, the vehicles are parked in tight formation and secured with lashings to keep them stable during ocean crossings. When the ship reaches its destination port, Nissan vehicles are driven off and placed into secure holding areas for customs clearance. Once cleared, they are transported to regional distribution centers. Here, a process called pre-delivery inspection, or PDI, is carried out. Technicians remove transport protections, recheck fluids and tire pressures, confirm there is no transport-related damage, and make any market-specific adjustments, such as software updates or headlight aim changes. Finally, the vehicles are dispatched to dealerships, where a last brief inspection is done before placing them on the showroom floor or preparing them for immediate delivery to customers. The moment a buyer takes the keys marks the end of the manufacturing journey, but for Nissan, the process is part of a continuous loop. Feedback from customers and dealerships feeds back to engineering and manufacturing teams, influencing improvements for future models. The highlight of this stage is the marriage, when the body is lowered onto the chassis assembly. Using synchronized lifts, the two halves are brought together, and fasteners are torqued to precise specifications. At this point, the Chevrolet vehicle has its structural and mechanical systems fully united. From here, connections are made between the body and chassis systems. Electrical hookups, fluid lines, control linkages, and exhaust mounts are all secured. Windows are bonded into place with high-strength adhesives, exterior trim and badging are applied, and final adjustments are made to doors, hoods, and trunk lids to ensure perfect fit and operation. To understand how a Toyota car is made, one must first step into a space where discipline, precision, and respect for process define every movement, the Toyota factory. Within these facilities, the transformation from raw materials to a fully functional vehicle is not simply a mechanical progression, but a living manifestation of a philosophy. This philosophy, known globally as the Toyota Production System, or TPS, is centered on two foundational pillars: Jidoka, automation with a human touch, and just-in-time manufacturing. Together, these principles dictate how every Toyota vehicle is born. Imagine walking into one of Toyota's flagship plants, such as the Tsutsumi plant in Toyota City, Japan, or the Georgetown facility in Kentucky. The air is filled not with chaos, but with a quiet, rhythmic hum. It is not the sound of urgency, but of synchronization. Workers, robots, and machines operate in precise harmony, each step of the process unfolding like clockwork. Every bolt tightened, every part aligned, every inspection performed. Nothing is rushed, but nothing is delayed. The objective is not to build fast, but to build flawlessly, and in the smallest increment of time and resource necessary. The beginning of any Toyota vehicle starts far upstream, not in the plant itself, but in the raw material supply chain. Toyota sources high-strength steel, aluminum, plastics, semiconductors, glass, and countless other materials through a tightly managed supplier network. Each supplier is held to stringent quality and delivery standards. Deliveries arrive at the plant just in time, often within hours of their use. This lean inventory philosophy reduces waste and ensures that the factory remains agile, able to adapt to shifting demands or changes in vehicle variants without maintaining massive backstocks. Once materials arrive, the first physical steps in vehicle creation occur in the stamping shop. Here, massive coils of steel or aluminum are loaded into enormous stamping presses, machines that weigh hundreds of tons and exert enough force to shape thick metal in a single, clean motion. These presses are fitted with die sets, precision-engineered molds that stamp out individual body components like fenders, hoods, roofs, and doors. The dies are swapped out by automated systems within minutes, allowing the line to shift seamlessly between models with minimal downtime, a critical capability in a mixed model facility. The stamped panels are then transported, often via overhead conveyor systems or autonomous carts, to the welding shop, the domain of the body in white. Here, the core structure of the car takes shape. Robotic arms, fitted with weld guns and sensors, orchestrate a ballet of sparks. These machines are programmed with exacting specifications to apply spot welds at predefined intervals, securing body panels together into a rigid, cohesive structure. Human technicians oversee the process, performing inspections, handling complex geometries, and activating andon systems, alert cords, should any defect be found. Toyota's concept of Jidoka is exemplified here. Each welding station is empowered to halt the entire line if a defect or misalignment is discovered. This is not seen as failure, but as a safeguard for quality. Rather than allow a potentially flawed product to progress, the issue is stopped at its source, analyzed, and resolved before production resumes. Workers are trained not just to follow instructions, but to improve the process. This continuous improvement culture, known as Kaizen, is deeply embedded in every team member, from entry-level assemblers to plant managers. Once the car body has been assembled and verified for dimensional accuracy using laser measuring systems, it proceeds to the paint shop, where it is cleaned, sealed, primed, and finally painted. Before any color is applied, the body is immersed in a series of baths for electro-deposition coating, a process that prevents corrosion by electrically bonding a primer to the metal surface. The body then moves through a drying oven before entering the color application booths. Inside the paint booths, robotic arms fitted with rotary atomizers apply successive layers of primer, base coat, and clear coat. Each coat is inspected under intense lighting and humidity-controlled conditions to ensure consistency and to prevent inclusions such as dust or overspray. Technicians perform visual inspections and touch tests, sometimes sanding and reapplying paint if surface imperfections are found. The body then enters a final curing oven, where it is baked at high temperatures to harden the paint finish. By now, the car's basic structure is complete and coated, but it still lacks its soul: the engine, drivetrain, electronics, and interior. These elements come together in the general assembly area, a zone that stretches across hundreds of meters and involves hundreds of interwoven processes. It is here that Toyota's just-in-time philosophy truly comes alive. Unlike traditional batch manufacturing, Toyota's production line is mixed model, meaning different car types and trims, even with different engines or drive systems, are produced on the same line in whatever sequence is dictated by real-time customer orders. To accommodate this, parts are delivered in sequence to the line. If the next car is a Corolla hybrid with a panoramic roof, the exact seat configuration, roof headliner, battery pack, and other components for that configuration arrive seconds before the car reaches the station where they'll be installed. One of the most critical events in the assembly process is known as the marriage, the point at which the painted body is lowered onto the pre-assembled chassis. The chassis includes the engine, transmission, suspension components, exhaust system, and drivetrain. These assemblies are built up in parallel lines and synchronized with the main body line so that both components arrive at the marriage station at precisely the same moment. As the body descends onto the chassis, guided by precision jigs and hydraulic lifts, technicians align mounting points and fasten critical bolts using torque-controlled tools. Every fastening operation is digitally logged and monitored. If a bolt is under or over-torqued, or if a tool slips, the system immediately alerts the operator. These digital confirmations ensure traceability and enable Toyota to maintain records for every car that leaves the factory, supporting future warranty claims, recalls, or quality assurance audits. After marriage, the car begins to take on its recognizable interior form. Dashboards are installed as single pre-assembled units, often produced by Tier 1 suppliers in nearby satellite facilities and delivered just in sequence. Seats, wiring harnesses, air conditioning modules, infotainment systems, and airbags are carefully installed in a series of tightly choreographed steps. Workers use a combination of hand tools, smart torque guns, and pick-to-light systems, which light up the exact part bins for each operation to ensure accuracy and speed. This process continues with the installation of glazing, lighting elements, bumpers, wheels, and various trim components. Every part is fitted under strict quality standards with gap alignment and surface flushness, checked visually and digitally using laser systems. During each step, workers remain empowered to pull the end-on cord if they detect an anomaly, reinforcing Toyota's belief that quality is built in, not inspected in. Once the assembly is complete, the vehicle is no longer a shell or a skeleton. It is a living machine but one that has not yet been proven. The next phase will test every system, calibrate every sensor, and ensure that the Toyota badge on the front carries with it the weight of reliability, safety, and trust. Following the completion of physical assembly, each Toyota vehicle enters one of the most critical phases of the production lifecycle, the inspection, calibration, and functional testing stage. This is where mechanical craftsmanship meets analytical scrutiny. Every car must now prove that it not only fits together correctly, but that every system operates as designed, with the precision and reliability Toyota is globally known for. The first area the vehicle enters is typically the initial quality gate. Here, a multi-point check is performed by trained inspectors who methodically examine structural components, body alignment, and basic mechanical fitment. Every door, trunk, and hood is opened and closed to assess alignment and sound. Uneven gaps, misaligned panels, or abnormal resistance are noted and corrected on the spot. Workers use gap gauges, flushness sensors, and manual inspection tools to detect even the smallest deviations in build quality. From there, the vehicle proceeds to dynamic system checks. This is where the car begins to come to life, electronically and mechanically. A technician connects the vehicle to a factory diagnostic system, uploading the final software package to all electronic control units. In a modern Toyota, there can be 30 to 80 ECUs depending on the model, each managing a different subsystem, such as braking, power steering, stability control, hybrid drive, airbag systems, and infotainment. The ECUs are flashed with firmware specific to the car's trim level, engine type, and market destination. This step is highly sensitive, with redundant data verification systems to ensure the software uploads completely and correctly. Once configured, the system initiates a global self-check, where the vehicle essentially performs a diagnostic scan of itself. Each ECU confirms its functionality and readiness, while the technician monitors for error codes or inconsistent behavior. Any anomaly is logged and triggers a deviation procedure where the vehicle may be diverted to a separate diagnostics bay for deeper troubleshooting. Next, the car is transferred to a specialized station for fluid filling and pressure testing. Here, automated systems dispense exact volumes of engine oil, brake fluid, coolant, washer fluid, and, for hybrid or electric models, inverter coolant or battery thermal management fluids. These filling stations are digitally calibrated to prevent overfilling or contamination. During this stage, systems are also pressurized and sealed, then tested for leaks using pressure sensors and flow meters. Brake lines are tested by pressurizing the system and monitoring for pressure drops, ensuring every car leaves with a perfect, air-free hydraulic system. At this point, the vehicle is ready for its first engine start. A technician initiates ignition using either a key fob or the factory diagnostic console. The vehicle turns over and the engine comes to life. During this brief but critical startup phase, the system monitors RPM, oil pressure, exhaust sensor feedback, charging voltage, and other vitals. The technician listens for abnormal engine noise, checks idle quality, and watches for leaks or warning indicators. Once the engine stabilizes, the vehicle begins a series of automated or semi-automated functional tests, including shifting through gears, verifying steering assist, and checking basic throttle response. With the engine running and fluid circulating, the vehicle now moves to the dynamic test track or rolling road, depending on the facility's layout. On a rolling road, a stationary test bench with rotating drums. The car is accelerated through a simulated driving sequence. Braking, acceleration, shifting, emissions control, and hybrid transitions are all tested under load. This is where software calibration is fine-tuned. For example, hybrid systems may be evaluated for smooth transitions between electric and gasoline power, while adaptive cruise control sensors are calibrated to recognize distance targets. Meanwhile, headlight aim is adjusted using laser-guided alignment equipment. Wheel speed sensors are tested, and the vehicle's onboard safety systems, such as ABS and traction control, are confirmed to respond appropriately to artificial inputs. On some high-spec models, even the sound insulation is checked using internal microphones while simulating wind and road noise inside a soundproof chamber. Following dynamic testing, the car is driven to a water test booth, an enclosed chamber equipped with high-pressure nozzles, positioned to simulate heavy rain, splash conditions, and high-speed water exposure. The entire vehicle is blasted with water from above, below, and the sides. Technicians inside the booth, or using moisture detection tools afterward, check the interior for any signs of leakage, particularly around doors, glass seals, sunroofs, and underbody grommets. Vehicles that fail this test are sent to a specialized sealing team for inspection and repair before re-entering the final inspection queue. The penultimate step in the process is the final visual and tactile inspection line, often referred to as the white light tunnel. In this area, powerful overhead lights and side lighting replicate broad daylight, revealing surface imperfections invisible under factory lighting. Inspectors move around each vehicle slowly, checking for micro scratches, paint defects, misaligned trim, dirt under the clear coat, and material inconsistencies. The tactile elements are just as important: seat firmness, stitching alignment, trim tightness, and even the smoothness of control knob rotation are checked against factory benchmarks. Finally, once all systems are verified, paint and finish are pristine, and data records confirm the vehicle's complete build and performance history, the car is released from production. A digital certificate is issued, containing every measurement, torque value, fluid fill, software version, and test result from each phase of assembly. This data is stored in Toyota's secure manufacturing archive and is linked to the vehicle's VIN for life. If a component recall, software update, or warranty claim ever arises, this record becomes the reference point for diagnostic and corrective action. As a last step, protective films are applied to vulnerable surfaces like the hood, doors, and bumpers to prevent damage during transport. The vehicle is then driven to the shipping yard, where it is scanned, parked, and queued for delivery via truck, rail, or ship, depending on its final destination. The birth of a Honda automobile is not an accidental fusion of metal, glass, rubber, and electronics. It is the physical realization of a manufacturing philosophy rooted in discipline, simplicity, and human respect. At the core of Honda's automotive production process is the concept of monozukuri, a Japanese term meaning making things with craftsmanship and pride. For Honda, monozukuri is not just about building cars. It's about building trust in every nut and bolt, in every weld seam, in every panel gap. To witness a Honda car being built is to enter a tightly orchestrated environment where technological sophistication meets manual precision. Inside one of Honda's production facilities, such as the plant in Marysville, Ohio, or the Sayama factory in Japan, the scale is staggering. These plants are sprawling ecosystems of autonomous vehicles, robotic cells, and human operators working side by side across multiple production halls. And yet, despite their size and complexity, the rhythm of the process remains surprisingly calm. Everything flows according to plan, governed by Honda's unique lean manufacturing philosophy known as the Honda Production System. The journey of a Honda car begins long before any metal is cut. It starts with production planning, a phase driven by market forecasts, dealer input, supply chain readiness, and model demand. Honda's plants operate on a build-to-order basis more than most automakers. That means production schedules are crafted based on actual customer orders and real-time market demand. This approach minimizes inventory waste and maximizes the efficiency of the supply chain. Once the schedule is locked in, suppliers across the globe begin preparing the thousands of components that will soon converge at the plant. Raw materials like steel and aluminum arrive at the factory in massive coils. These materials first enter the stamping department, a cavernous space filled with towering hydraulic presses. Each press is fed with sheet metal and fitted with enormous dies, complex mold tools shaped to form specific vehicle panels, such as hoods, doors, roofs, and fenders. The dies are interchanged automatically using massive overhead cranes and quick change systems, allowing the factory to shift between different vehicle models with incredible speed. These presses apply thousands of tons of force in milliseconds, transforming flat sheet metal into high-precision components with reinforced curves and load-bearing geometries. Each stamped panel is checked using template gauges or laser measuring arms to verify its accuracy against design tolerances. Honda's emphasis on dimensional precision at this early stage ensures that all panels fit perfectly during final assembly, which in turn improves both structural integrity and noise insulation. The stamped panels next travel to the welding shop, where the vehicle's skeleton, known as the body in white, is assembled. This stage is a symphony of automation. Dozens of robotic arms arc and swivel across each cell, welding panels together with pinpoint accuracy. These arms are fitted with spot weld guns, seam welders, laser cutting tools, and even rivet actuators, all pre-programmed for the vehicle model and trim level currently on the line. Guided by 3D coordinates, these robots can perform hundreds of welds in just a few minutes. Despite this high degree of automation, human workers play a vital role. Technicians monitor robotic operations, inspect weld seams visually, and perform manual welding in areas where robots cannot easily reach, such as complex internal joints or tight cavities. Importantly, Honda applies its stop-the-line authority in this department. Any associate who detects an issue is empowered to halt the line and initiate corrective measures immediately. This is part of Honda's respect for humanity approach, trusting operators not just to follow instructions, but to contribute actively to product quality. Once the weld shop produces a complete body shell, it enters the sealing and corrosion protection area. At this stage, structural adhesives and sound dampening materials are applied to critical areas of the body, such as the floor pan, roof seams, and door frames. These materials increase rigidity, improve crash performance, and reduce road noise. Seams are also sealed with flexible gaskets to protect against water ingress. After sealing, the body is conveyed to the paint shop, one of the most technologically advanced sections of the plant. Before any color is applied, the car is submerged in a series of cleaning and surface preparation baths. These include alkaline washes, acid baths, and a crucial e-coating step, in which the entire body is dipped in an electrically charged primer solution. The electrical current causes corrosion-resistant particles in the bath to bond uniformly with the metal, even in hard-to-reach crevices and weld joints. Once the e-coat is cured in an oven, the body enters a clean room environment for the color painting process. Robotic arms with electrostatic spray guns apply the primer, base coat, and clear coat in successive layers. Each layer is air-dried or heat-cured to ensure optimal adhesion and durability. Honda's paint robots use feedback-controlled nozzles that adjust spray patterns dynamically based on body shape and angle, reducing overspray and minimizing environmental impact. Between layers, the vehicle is visually inspected under specialized lighting conditions. Technicians look for drips, dust contamination, and color uniformity. If any issues are found, the body is flagged for manual repair, which may include sanding, buffing, or repainting a specific panel. Once painting is complete and the final clear coat has cured, the body is ready for general assembly, the stage where it transforms from a painted shell into a fully functioning automobile. Before reaching the general assembly line, however, many key sub-assemblies are built in parallel feeder lines located throughout the plant. These include engine and transmission modules, suspension components, dashboards, interior trim sets, seat assemblies, and wiring harnesses. Honda practices a synchronized sub-assembly strategy. Each of these components is produced and sequenced in real time to meet the exact build order of the cars progressing down the main assembly line. That means if car number 287 is a Honda Accord hybrid in touring trim, every part of that specific configuration is queued and ready to install by the time the body reaches the relevant station. When the painted body reaches the main assembly line, it is mounted onto a moving conveyor system. This conveyor will carry the vehicle through dozens of stations, each performing a specific set of installations or tests. The first few stations focus on interior preparation. Sound deadening mats are applied to the floor. Wiring harnesses are routed through the firewall and chassis, and the dashboard is bolted into place. Honda uses pre-assembled dashboard modules, which include the instrument cluster, HVAC system, infotainment screen, and most switches, all pre-tested before installation. This reduces line complexity and improves consistency. Seats, carpeting, door panels, and airbags follow shortly after. At every step, workers use a system of digital instructions, torque control tools, and pick-to-light part bins to ensure that the right part is used and installed to the correct specification. Honda's goal is zero deviation from build order, even in mixed model lines, producing different trims every few minutes. As interior installation continues, the process becomes more intricate. With the dashboard now secured, the vehicle receives its electrical control units, sensors, and remaining interior electronics. These are connected to the pre-installed wiring harnesses using color-coded, click-locked connectors that help eliminate the possibility of human error. Specialized quality control stations may test critical modules immediately after connection, especially airbag sensors and crash detection systems, to ensure they are responsive and correctly integrated into the vehicle's network of ECUs. Following this, attention turns to glazing and weather sealing. Robots or trained technicians carefully install front and rear windshields, applying adhesive in a uniform bead to ensure a perfect seal. The installation is timed precisely as the adhesive cures rapidly. Door windows, quarter glass, and side mirrors are added next, with their mechanisms tested on the spot to ensure smooth operation. Throughout this process, jigs and fixtures are used to maintain tight tolerances between the panels and glass, ensuring aerodynamic integrity, road noise insulation, and weather protection. The vehicle then reaches one of the most pivotal points in the production process, the powertrain marriage. As the body travels down the assembly line, a pre-assembled drivetrain module consisting of the engine, transmission, front or all-wheel drive differential, and suspension subframe arrives underneath on a separate conveyor. The marriage station uses synchronized hoists and laser-guided platforms to lift the body and lower it gently onto the drivetrain assembly. Once aligned, operators bolt the body to the subframe using hydraulic torque tools, which log each torque application in real time for quality traceability. The process of mating the body to the chassis and powertrain is more than a mechanical operation. It's an integration of identity. From this moment, the car ceases to be a shell and becomes a functional vehicle. After the marriage, systems are connected. The fuel lines, brake lines, wiring looms for sensors and control modules. Axles are bolted in. Radiators and intercoolers, along with their coolant hoses, are fitted. Exhaust systems are clamped into place and routed along the underbody using guides to prevent rattle or contact with heat-sensitive zones. Next come brake systems and suspension components. Brake calipers and discs are attached at each corner, followed by routing and fastening of hydraulic lines. ABS sensors and wheel speed sensors are snapped into their mounts, and their cables are clipped securely to avoid movement. Meanwhile, shock absorbers, coil springs or struts are fastened to the body using calibrated robotic arms or torque-controlled tools operated by line workers. These fasteners are critical as they influence ride quality, safety, and steering behavior. The wheels and tires, pre-mounted and balanced in a separate line, are then delivered just in time to the vehicle. They are aligned to the hub assemblies and fastened using pneumatically powered tools equipped with digital torque sensors. Each wheel torque is logged and checked against specifications. Even minor deviations trigger alerts. For instance, over-tightening a lug nut can damage threads or warp brake rotors, so precision is not optional. By this stage, the vehicle is mechanically complete, but not yet operational. It now passes into a startup and calibration zone, where the first true interaction between systems begins. Trained technicians perform a key-on sequence where all electronic systems are activated. This step includes powering up the main vehicle bus, initializing communication between ECUs, and performing a cold test of lighting systems, instrument clusters, wipers, and cabin electronics. The technician uses a diagnostic console to verify proper communication between modules and applies any last-minute software updates if required. Once the vehicle's systems are verified and error-free, the engine is started for the first time. A moment that is both mechanical and symbolic. As the engine cranks and catches, onboard diagnostics immediately monitor oil pressure, exhaust emissions, idle speed, coolant flow, and electrical charging. If any of these parameters fall outside of the calibrated range, the system flags the vehicle for further inspection. For hybrid models, the electric drive system may initiate instead, with the gasoline engine starting only after the battery state of charge reaches a specific threshold. After the successful start, the car enters the rolling road test or chassis dynamometer. Here, it is strapped to large rollers that simulate road conditions. The car is driven through a standard cycle of acceleration, braking, shifting, and cruising, all while remaining stationary. This test evaluates key systems including ABS, traction control, throttle response, gear engagement, hybrid transitions, and engine tuning. Sophisticated sensors and computers monitor hundreds of data points per second, ensuring the vehicle performs exactly as designed. Following the rolling test, the vehicle undergoes a headlight alignment and safety calibration station. Here, laser-guided systems measure the alignment of headlamps, and adjustments are made to meet both manufacturer and regional regulations. Advanced driver assistance systems such as lane keeping assist, adaptive cruise control, and forward collision warning are also calibrated at this point. This is accomplished using visual targets placed at known distances and angles in front of the vehicle, allowing cameras and radar units to learn their field of vision relative to the car's center line. Once these tests are complete, the vehicle proceeds to the water leak test booth, a sealed chamber equipped with an array of high-pressure water jets. For several minutes, water is sprayed at every angle, above, below, and from the sides, mimicking hurricane-force rain. Technicians inspect the cabin interior afterward for leaks, particularly around window seals, sunroofs, and door frames. Any sign of moisture sends the vehicle to a sealing team for immediate remediation and retesting. The car now moves into the final inspection area, often referred to as the white light tunnel. This zone is illuminated by intense, color-corrected lighting systems that reveal even the smallest defects in paint, fitment, and alignment. A team of inspectors walks around each vehicle, using mirrors to check lower panels, feelers to check panel gaps, and gauges to measure surface flushness. They assess the finish of paint, the gloss consistency, the evenness of door gaps, and the snugness of interior trim. Particular attention is paid to areas around weld joints, door hinges, and tailgate edges where minor misalignments can occur. Each inspector has the authority to flag the vehicle for any observed issue, no matter how small. Flagged cars are moved to a rework area where expert technicians resolve any concern before the vehicle can be released. Rework stations are not viewed negatively. They exist to ensure that every vehicle that exits the factory is indistinguishable from one that passed cleanly through all stages. After final inspection, the vehicle is prepared for delivery. Protective plastic sheeting is applied to painted surfaces and interior areas prone to contact during transport. The car is then driven to a shipping lot, where it is scanned into inventory and parked according to destination. Vehicles headed for domestic markets are grouped by dealership region and loaded onto transport carriers, while those bound for international markets are routed toward ports and loaded onto ships. The Honda factory's job may seem finished here, but in truth, its responsibility continues well beyond the factory gates. Each car's production data, including every torque value, software version, fluid fill level, and test result, is linked to its unique vehicle identification number and stored securely in Honda's manufacturing cloud. If an issue ever arises in the field, Honda can trace it back to the exact moment and operator involved in the car's creation. To witness the making of a Ford vehicle is to observe the evolution of industrial craftsmanship, a living embodiment of the assembly line system first pioneered by Henry Ford over a century ago, and refined today into a symphony of automation, digital intelligence, and human engineering. In modern Ford factories, like the Rouge Complex in Dearborn, Michigan, or the Oakville Assembly Plant in Ontario, production isn't simply about building cars. It's about orchestrating a precisely timed flow of materials, people, and machines that together transform raw components into advanced, drivable technology. The process begins long before the first bolt is turned or the first panel is stamped. The foundation of Ford's modern production system lies in rigorous planning and global coordination. Ford operates with a just-in-time and just-in-sequence supply chain strategy, meaning that materials and components arrive at the factory floor moments before they are needed. This eliminates the need for large stockpiles of inventory and increases the plant's flexibility to respond to changes in production schedules or model configurations. Planning starts with demand forecasting and order management. Using a centralized production planning system, Ford determines what models, trims, colors, and drivetrain variants will be built on any given day based on global dealer orders, regional demand patterns, and parts availability. This build mix is then converted into a master schedule that guides every action in the plant, from how robots are programmed, to which parts are loaded into which bins on which carts. At the heart of every Ford plant lies the stamping facility, where large rolls of sheet metal, primarily steel and aluminum, are cut and formed into individual body panels. These sheets arrive from external suppliers and are checked for thickness, flatness, and coating quality before entering the production line. Inside the stamping area, massive hydraulic or mechanical presses, sometimes up to 30 feet tall, use high tonnage force to shape the sheets into components such as hoods, roof panels, fenders, doors, and floor pans. Each stamping press contains tool and die sets, which are the sculpted steel molds that give shape to the metal. Changing these dies can take several hours on older systems, but Ford's modern plants use quick change tooling and automated die swapping cranes, allowing multiple model variants to be stamped in a single shift. Once stamped, each panel is inspected using automated vision systems and tactile measuring tools to ensure dimensional accuracy and surface quality. These stamped parts are then sent via conveyor or robotic shuttle to the next critical phase: body construction. In the body shop, robots dominate the floor. Here, the car's skeletal structure, called the body in white, is assembled from stamped panels. Using a combination of spot welding, MIG welding, and adhesive bonding, robots join together hundreds of individual panels to form a rigid structure that meets crash and durability standards. Each robotic cell is carefully synchronized, with arms moving in mirrored patterns to weld seams, attach reinforcements, and secure structural elements like the rocker panels and cross members. The entire body structure is periodically scanned with laser measurement systems. These 3D scanners create digital models of the assembled body to verify that it remains within tight tolerances. Even the smallest variation, fractions of a millimeter, could cause issues with later stages, such as door alignment or windshield fitting. If a body is found out of spec, it is automatically flagged and removed from the line for correction or further inspection. While the robots do the bulk of welding, human operators in the body shop play crucial roles. Some welds require access to tight spaces that robots can't easily reach. In addition, skilled technicians perform tactile inspections, feeling for uneven surfaces, sharp edges, or anomalies that a vision system might miss. They are also empowered to stop the line using an andon system, a visible alert mechanism that signals an issue requiring immediate attention, a practice inherited from lean manufacturing disciplines. Once the body is complete, it's sent to the paint shop, a sealed and environmentally controlled environment that is perhaps the most intricate and sensitive area of the plant. But before paint can be applied, the body must be cleaned, prepped, and protected. It first enters an electrodeposition tank, or e-coat bath, where it is submerged in a liquid anti-corrosion primer. An electric current causes this primer to bond uniformly to every surface of the body, inside and out, including hidden cavities where rust could otherwise form over time. After curing in an oven, the body moves into a multi-stage painting process. Robots apply layers of primer, color, and clear coat using electrostatic spray guns, which attract paint particles to the metal surface like a magnet. The advantage of this method is increased efficiency and reduced overspray, leading to lower paint consumption and a cleaner environment. Ford's paint booths are equipped with air filtration and humidity control systems to eliminate dust or contaminants that could mar the finish. At each stage, lighting conditions are precisely calibrated to reveal imperfections, and technicians are stationed throughout the booth to perform quality checks. If a blemish is detected, a run in the paint, an uneven finish, or a missed spot, the vehicle is diverted to a paint repair zone where the affected area is wet sanded, resprayed, or polished by hand to meet Ford's appearance standards. After the final coat, the body undergoes a final curing process in a high-temperature oven to harden the paint and create a durable, glossy finish. The now fully painted vehicle shell, known as the trimmed body, advances to the general assembly line. This is the most labor-intensive section of the factory, where machines and humans collaborate closely. Unlike the body shop, where robots dominate, the general assembly area relies more heavily on human hands, precision tools, and ergonomic aids. The car body is mounted on a moving conveyor system known as a skillet line or friction drive platform, which carries the car through a series of workstations at a constant, carefully controlled speed. Assembly begins from the inside out. First, teams install insulation pads and sound deadening materials. Next, wiring harnesses, which form the car's electrical nervous system, are laid out and clipped into position along the floor, firewall, and side panels. Each harness contains dozens of connectors that will link to ECUs, lighting elements, climate controls, sensors, and powertrain systems. Proper routing and fastening of these cables are essential for both performance and safety, so visual checks and scanner-based validations are used at multiple points. Then comes the dashboard module, which is typically pre-assembled in a nearby subline. It includes the steering column, HVAC ducts, infotainment screen, and instrument cluster. This large component is inserted into the cabin as a unit using mechanical arms and then bolted into place. Seats, carpeting, interior trim panels, seatbelt retractors, airbags, and roof liners follow, each added in a precise order, with visual and tactile inspections performed continuously to ensure flawless fit and finish. Throughout this interior build process, Ford uses error-proofing tools such as torque-controlled wrenches, pick-to-light bins, and vision-guided assist arms. Every torque application is digitally logged. If a bolt is over or under-torqued, the system automatically halts the line and flags the issue. This traceability is vital, not only for quality assurance, but also for future diagnostics should the vehicle need service or become subject to a recall. Continuing from the general assembly line, the next transformative step in the creation of a Ford vehicle is the marriage of the painted body with the powertrain and chassis systems, a defining moment in every car's life on the line. As the body shell makes its way along the conveyor, the fully assembled engine, transmission, suspension, and front subframe approach from a lower parallel track. These components, built and tested in a separate sub-assembly area, are synchronized to arrive at the exact moment when the body reaches the marriage station. Here, specialized lifting systems raise the powertrain module from below while the body is gently lowered from above. Technicians, supported by robotic arms and torque-controlled tools, fasten the body to the chassis at critical mounting points. This precise alignment is essential. It determines the geometry of the suspension, the drivetrain angles, and even the behavior of noise and vibration through the cabin. Fuel lines, coolant hoses, drive shafts, brake lines, and wiring harnesses are then connected between body and chassis, integrating the mechanical and electrical systems into a unified vehicle. After the marriage, the vehicle receives its cooling system, air intake, and exhaust components, followed by fluids, including engine oil, brake fluid, transmission fluid, and coolant, all filled using automated dispensers that monitor volume, pressure, and flow rate. These filling stations ensure consistency down to the milliliter, and if there is any deviation from the programmed values, the system stops the process and flags the vehicle for investigation. With the engine installed and fluids topped off, the vehicle is now nearly complete. It receives its wheels and tires, which are pre-mounted, balanced, and matched to the specific trim and model variant. These are installed using torque monitoring impact wrenches, and the system logs each wheel's torque values in the vehicle's digital build record. Exterior components such as bumpers, lights, badges, grille assemblies, and mirrors are now added, bringing the vehicle's final form into view. At this stage, the car has all its physical components, but it still needs to come to life. The next section of the line is dedicated to initial startup and systems calibration. A technician connects the vehicle to a diagnostic console and performs the first ignition sequence. This process powers up the ECUs, activates safety systems, and starts the engine. Immediately, a flood of data is captured: oil pressure, engine RPM, voltage, emissions readiness, and more. The technician watches for warning lights, verifies software synchronization, and confirms that all onboard systems are responsive. If all readings are within specification, the vehicle advances to functional testing, where every major system, lights, brakes, steering, wipers, infotainment, HVAC, and electronic safety aids, is tested in a rapid, choreographed routine. Ford technicians use handheld devices and sensor panels to trigger functions and confirm their proper operation, all while the vehicle moves slowly along the inspection path. Any anomaly here diverts the vehicle to a diagnostics bay for further analysis.